All right, we're going to go ahead and get started. Welcome to day 2 of the IEP workshop in 2026. Once again, my name is Adam Naniga. I'm with the U.S. Fish and Wildlife Service out of Lodi. So there's a QR code at the registration table that'll get you the agenda. It'll also share information about the after hours event and the get to know workshop attendees bingo game. So be sure and check that out. There's also hard copies of the bingo game in front of at the registration desk. The bathrooms and water fountains are on the west side of the building under the stairs, and on the second floor, right at the top of the stairs to the right. The poster room and overflow room are at the top of the stairs and to the left. The overflow room is adjacent to the posters. A little bit of safety information. If we need to evacuate the building, please walk calmly and quietly to the nearest exit. Right there, and back there. Our designated gathering station is 1615 9th Street. So in an emergency, we'll assemble there and remain there until told otherwise. The Wi-Fi in the building is March 2026. That's a lowercase m. Once again, there's no food or drink in the auditorium. We really need to keep this space clean. So please, no food or drink. If you're gonna eat or drink, please be in the lobby. Our coffee and tea bar in the lobby is sponsored by ICF. Thank you for that, ICF. If anybody needs any kind of accommodation, such as the elevator, access to a lactation room, or a hearing device, please see Christine Job at the front desk. For our online audience, since this is a hybrid event, we will be taking questions both online and in person. If you're online, please fill in your questions in the Q&A box. And if there's time, we'll get to them. This workshop is being recorded, so assume anything you ask during the Q&A will also be recorded. However, there are 4 presentations that are not recorded, and therefore the Q&A will not be recorded. There's no sitting on the back ledge like the windowsill. So if you're in this room, you should either be sitting in a seat or you can stand in the back. For today, we have 2 excellent plenary speakers that will be speaking from 8:35 to 9:35. We're going to take a 15-minute break. And then we have Delta and Longfin Smelt session from 9:50 to 10:50 a.m. And then another second Delta and Longfin Smelt session from 11 to noon with a 10-minute break in between those 2 sessions. Lunches from noon to 1:30. This afternoon at 1:30, we'll have a session on physical and biological effects of flow. There'll be a short break, and then 2:50 to 3 p.m., Zooplankton and other invertebrates session from 3 p.m. to 4 p.m. And then poster session after 4. So we do, thanks to Peter Nelson for setting up the after hours event at Sacramento Pipeworks. So it's climbing followed by a visit to the nearby microbrewery, and that's 116 at North 16th Street. And that'll be immediately following the workshop. So we have, like I said, we have 2 plenary speakers. Trinh Nguyen will be our first plenary speaker of the day. Trinh is a fish biologist and data scientist with the California Department of Fish and Wildlife's Bay Delta office. His work focuses on the complex human ecosystem balance of the estuary, specifically looking at how we bridge the gap between raw data and biological insight. To do this, Trinh relies heavily on ecological modeling, tool development, and data synthesis. His work is a constant loop of searching for ways to augment our biological expertise with computational power. That philosophy of using systems to extend our capabilities is the heart of his presentation today. He is here to discuss how we can use generative AI to reduce technical bottlenecks and enhance our study of the Bay Delta. Thanks, Trent.
Thanks, Adam. Hi, everyone. So it's been fairly interesting for me to watch our community try to adopt a new technology fairly early on for once. And I think that speaks volumes to how potentially transformative this technology really is. And I, for one, do believe that the excitement is very well justified. And so this is the augmented biologist using generative AI for technical workflows and exploration. Oops. So a quick roadmap of the presentation. I'll first talk through some goals that I have for this talk. I'll then go into defining what generative AI is, and I'm not going to go into the technicals. I would refer you to Carl's presentation yesterday for that. After that, I'll talk about some obstacles to adoption of this technology. And then I will spend the bulk of the presentation talking about the mindset shift that we need to adopt in order to utilize this technology in our technical work. What's useful for us, one is in increasing our efficiency, and the second is to increase our ability to explore ideas. After that, I will conclude. So I have two main goals for this presentation, and they're fairly straightforward. The first is just to understand what are the opportunities available to us because of generative AI. And then the second is to then successfully try to integrate generative AI into our technical workflow. So what is generative AI? If you were here yesterday, you should know what generative AI is. But essentially, generative AI is synonymous with large language models, or LLMs, or you might know them a little bit more via their model names themselves. So ChatGPT, Claude, Gemini, those are all generative AI models. And to me, Gen AI is essentially a generational scientific tool that has become available to us as scientists. It is essentially a tool that is designed to augment our own expertise as a scientist, not to replace it. So I view it as equivalent to a scientist when they first learn how to use the personal computer for their work, or when they adopt software like Excel, GIS, or R in their scientific workflow. I think it's truly transformative, and I think we really do need to start considering how we should be able to use it in our work. So before I dive deeper into how we can use it in our work, I just want to take a step back a bit and talk about some of the obstacles that do exist to adoption. And these are things like organizational use policies, which move at the speed of bureaucracy. So who knows how that is going to play out. There's monetary costs associated with this. If you wanted to use the latest and greatest models from these labs, you're probably going to have to pay a monthly subscription. And then there are obviously ethical concerns about the training and use of these models, things like resource use and potential inherent biases that these models learn based on how they are trained. These are all barriers that do exist, and I just wanted to bring them up, but I won't have time to really dive into them today. What I do want to focus on is this barrier of unfamiliarity and the stigma that you may be cheating if you are using generative AI to produce the products for your work. And I think this feeling of shame stems from the fear of the black box, from a lack of understanding of how these generative AI models work, and thus an inability to explain and reproduce what the model has produced for you. And I think at a high level that this isn't really the case. At a high level, these models, how they arrive at their conclusions, their outcomes, are very similar to something that we as scientists know very well, and that is the scientific method. And so specifically, the observation and question step here, this is your prompt to the generative AI system. From there, the AI is going to grab all that context and is going to move into the research step, which is where it will look at the training that it has already done to pull all the relevant information to potentially answer your question. After that, it goes into the reasoning phase, which is the hypothesis testing and analysis steps of the scientific method. Essentially thinking step by step through your questions, looking at all the data that it has been trained on, using tools to pull in additional data that it may be missing to then try and generate the best possible answer to your question. After which it goes into the inference phase, which is the reporting step of the scientific process. And so at a high level, I'd like to just point out that it does try to mirror the rigor of the scientific method when it is trying to decipher what you are asking it and developing a question for you. And I would like to just highlight that, like the scientific process, this process is also iterative. You shouldn't expect to get the perfect answer just after one round of prompting, just as how you wouldn't expect to find the perfect answer after one round of experimentation. Now, something else that we as scientists are really familiar with is this aphorism that all models are wrong, but some are useful. And we've been trained to view all models with a critical eye. And at the end of the day, these Gen AI systems are simply statistical models. And so we should treat them like how we should treat our models, that they are potentially highly useful, but we should trust them with a grain of salt. And so if we're able to see that these are potentially useful tools, but also potentially wrong, then I think it helps us with adopting this mindset shift that I think is necessary to use this system correctly in our technical work. And essentially, we've been misled by the term artificial intelligence. And I think it's just a marketing gimmick that these tech companies have thrown at us, because artificial intelligence means that there's automation involved. And unlike you and I, these models cannot have a spark of curiosity that then sets off a scientific method. Everything that they do still requires our active guidance in order to work. And so that means we should flip the way that we see these models. So instead of seeing them as AI models, we should see them for what they are, and they are IA models, which are intelligent augmentation models. This means that they are tools that are there to help extend and enhance our own abilities and capabilities. And there are two main areas where I think Gen AI is really helpful for us. One is to increase the efficiency of our work, and two is to explore ideas. So for efficiency, in our minds are various ecological understandings of how the world potentially works. And what we do as scientists is then to try and translate that understanding into code to test, text to communicate. But to get from point A to point B is really difficult. There's a lot of friction that exists to get there. And you can think of that as an implementation tax. There's heavy cognitive and temporal cost required for this translation. And luckily, I think we can use generative AI to pay down this tax. And there are three main costs associated with this that I think we can use AI for. They are volume, execution, and communication costs. So volume cost, this is your literature review. This is where you go and read the seminal papers to better understand the context of your observation or question. Gen AI has been trained on all these papers. And when you combine that with the computational speed that they are capable of, they are really good at aggregating and explaining broad concepts from the corpus of human knowledge. And some of you might have tried this in the past and have been turned off by the fact that sometimes these models do make things up. It's called hallucination. And hallucinations still exist today in the frontier models, but I would say that they are a lot more robust to hallucinations than ever. And there exists tools that they can lean on to mitigate that even further. Now, helping to pay execution costs. I think this is the most straightforward use of Gen AI. If anything, generative AI can be seen as the ultimate universal translator. And what we're doing as scientists is trying to translate that ecological understanding in our head, trying to take that and translate it into computer language to test and into natural language to communicate, which means that generative AI is the perfect fit for this. It's also very helpful to decipher computer language back into natural language for us to better understand what we're doing. Communication costs. So writing is really difficult, especially when you have very complex methods and results that you want to portray clearly to your audience. But these are language models, and so they are built to produce text. But writing is also an art form that is specific to you and to the situation that you are in. And so I actually don't advise you to use AI, Gen AI, as a primary author. What I think is really useful for is to use to construct structural scaffolding to organize the chaos in your mind. And you can do this in three main ways. The first is just to take a brain dump of the raw thoughts that you have, throw it into the model, and ask for a logical outline. From that outline, you can then create a rough draft and then throw that rough draft into the model and ask for a reverse outline. This helps you look at the structure of your writing to see if there's redundancies, if there are logical flaws in your thinking. And then finally, once you get towards the end and you have a final draft, you can use Gen AI to resolve grammar and conventions, tasks that have very clearly defined rules and answers are something that Gen AI is really good at doing. And I think you can use them directly for that kind of thing. So those are ways that you can use, those are practical ways that you can use Gen AI for efficiency. Next is Gen AI for exploration and the ideation step. So ecology is obviously rarely deterministic, and this is because our data is never perfect. And so we have to, at the start of a project, be fairly creative in how we approach those problems. And generative AI has essentially been trained on all of those potential methods, or most of those potential methods, unless you're a superstar and you're working on something truly novel. But the flaw is that these models, as they are trained to be people pleasers. And so they are not very good at pushing the boundaries. And so they're not very good at helping you through this ideation process. And so luckily, the simple solution here is something called persona prompting, which is you explicitly telling the AI to take on a specific role, because this forces the model to narrow down into a specific domain and make it extremely useful, more useful for our technical work. There are three main personas that I've found useful in my technical work. The first is to ask it to be a collaborator. And this is very useful at the beginning of your project. When you're exploring ideas, you can ask it for established or divergent ideas on how to approach things. You can also use it as you're going along in your project to serve as a cognitive mirror that you can just throw ideas on and see if what you're thinking through makes sense or not. The second is to ask it to be a reviewer or a devil's advocate. This helps you stress test through your reasoning. This helps you evaluate your methods against what are best practices and assess the model validation assumptions that you may miss along the way. And then finally, you can ask it to be a tutor. Again, generative AI is, if anything, a universal translator. And complexity is simply a knob that it can turn up or down. And so you can then pair that with the fact that they essentially have infinite patience. So as long as you have curiosity to pay, you should be able to learn anything you want. Okay. And so those are practical ways to use Gen AI for efficiency and exploration, but they all follow this framework, this general framework of the sandwich method, which says that the first step, the first slice, is the human slice. This is where you define the scope and the context and the persona that the model should take on to do what you want it to do. That then goes into the second step, which is where the AI is used to execute what you have asked it to do. And this leverages its knowledge base and executional speed. And then that gets routed to the last step, which is, again, comes back to you, the human, to verify, clarify, and edit the results that the AI has provided you. And there's two things that I want to highlight here. The first is that AI in this case, in this framework, is used specifically as a tool to help you within your workflow. And the second is that it's an iterative process. You shouldn't expect the AI, the product that the AI produces is going to be perfect. You're going to need to verify that it's giving you exactly what you're wanting. And you might need to go back and edit that. And so like any scientific tool, you should assume that it will work for you, but you should remain vigilant that it is working correctly. And so to start wrapping up, there seems to be this gap in productivity between users who use Gen AI and see a massive increase in productivity and those who use Gen AI and don't see the same increase in productivity. And I think this gap is basically a matter of mindset. I think that people who are using Gen AI and are productive are seeing Gen AI for what it is, that it is an IA tool that you're using to help you with your work, that you're actively guiding, and that it is not an oracle that you're trying to seek the right answer from. And the nice thing about this mindset is that it also means a tool can never replace its user. And it gives you some immunity against the doom and gloom that AI is going to replace us all. And so, in closing, I just want to reiterate that I truly think this technology is transformative. And I really implore you all to try and integrate IA into your daily practice. Use it, treat it as a second brain that's basically on standby when you are working. And for me, it's on 24/7 now whenever I am working. And I will throw ideas to it if I have a curiosity. And like anything, there is a learning curve associated with the use of Gen AI. But the beautiful thing about Gen AI is that you can traverse that curve simply by coding in natural language. And so all it takes is curiosity. And so I'll leave you with some suggestions if you don't know where to start on where you can get started today. You can take an old script and ask for a refactor or an annotation to see what you've done in the past. You can take a paper that you're very familiar with and ask for a summary to see how it's done. Or if you're feeling really spicy, you can take a topic that you think you are an expert in and ask for the AI for a riveting debate. So hopefully all of that leads you somewhere, and hopefully it leads you to a more productive future.
All right, we do have about 10 minutes for questions.
That was a 20-minute talk.
Yeah. Please make sure you have a microphone when you ask a question. And there's one online.
Good morning. That was very helpful. I've been struggling with using AI mainly for coding and for looking up stuff. But the problem I've had is that it tends to write code that's too elaborate. It's too complicated and too fancy. And it wants to throw in a million things that I didn't ask for. So it'll say, it'll try to go to the, I want this answer. And then it'll go to the next step. You can take that answer and do this and this and this and this. How do you keep it from doing that? Or how do you work with it to not do that?
Yeah, that's a really good question. And I think it depends on how you approach it. I think if you ask the AI for a very large, if you ask the model to make very large steps, then it will give you code that is a little bit too complicated. And so I think it depends on how you set up the system. I think if you're able to drill down specifically what you want the AI to do, be a little bit more specific in your request, then it becomes a lot more comprehensible. And I think this is where you as a scientist benefit from having more expertise in the process. The more expertise you have, theoretically, the finer that you can understand that process that you want to get to. And at that point, you're just basically leveraging generative AI to execute for you. But I do find that if you ask it a very broad question, it will potentially skip steps, and it can give you code that is a little bit too complicated or fluffy. You can also, I find that you can also ask it for a refactor, which then tries and simplifies the code that it has provided you. Or throw it into another model and take that output from one model, use another model, and ask it for another perspective. And that's essentially having another mind give an opinion on what has been provided to you.
What about writing text? It's a bit daunting in a way because of the problem of who's the author.
Yeah, for sure. I think writing is really difficult because, like I said, I think it's an art form. And everyone writes differently, and everyone thinks good writing is different. And these models are trained to give very generic answers because the generic answers is going to meet the needs of most people. And so if you can, there are ways to make it more tailored to how you want to write. You can provide it with examples of writing that you think are useful, and it can try and emulate the way that you write a little bit better. But I think it all comes back to the fact that you need to understand your own writing style, and that needs to be communicated. That context needs to be communicated to the model. Otherwise, you will get very generic writing.
Hi. Thanks, Trinh. That was a great talk. Really appreciate the walkthrough of how we can incorporate this into our work. I'm wondering how much, someone who might be new at this needs to research exactly which of these tools we should be using and know what it's trained on. You mentioned that, these models are trained on all of the wealth of the scientific literature. However, it doesn't have all of that in its training data. Some of it, it's going and researching. Different models will be trained on different data. So how do we go about choosing which of these AI tools we use? And how do we find out what data it was trained on and what we need to tell it to go and research on its own?
Yeah, that's a really good question. So I think personally, any of the large models, the major models, so ChatGPT, Claude, or Gemini, are going to be able to give you results that are satisfactory. These are frontier models, and essentially they have a 3-month horizon after which they will be updated. That doesn't mean that the knowledge cutoff is going to be updated, but they themselves will be updated. And the larger these models get, the more comprehensive and capable they are. But when you start using these models, you do find nuances to what some models are good at and some are not good at. Like Claude, for example, is really good at coding compared to the other models. And so I think you can just start with any of them, honestly. Start with any of them as a starting point, and then as you learn, you will find that there are nuances that will bring you to a model or not. But for me, I just stick with Gemini. Right? And I think the model is powerful enough, robust enough to give you those answers that you seek. And if they are answers that are beyond its knowledge cutoff, there are tools like Notebook LM, which is basically what I use to produce these slides, that you can use to basically ground truth the model even more. Notebook LM, for example, allows you to upload all the relevant information documents that you want the model to pull directly from And that allows you to ground truth the model even more. And so these models are now robust enough where you can start utilizing these tools to make it a little bit more robust to exactly what you want it to do.
Thank you for that talk. It was very interesting. I just wondered, it's great for coding, but I wondered what sort of barriers you're seeing in institutions and agencies about using AI, because it's a two-way thing. That when you produce things, if you're producing a paper that could have some confidentiality, that there's a lot of rules in place. So I just wondered, what sort of barriers are you seeing from your perspective?
Yeah, the organizational use one is really a difficult obstacle. I think most agencies or organizations are really protective of their data. And because of that, it may be limiting on what you can do with these models. As in, if you may not be able to upload directly your data to these models. So instead, I think what you should be using these models for is just the frameworks, developing the frameworks on how to approach these models instead. I think the bureaucracy associated with your organization and how you can use these models is a little bit too slow for how fast these models are developing and how potentially useful they are in your work. And so I would just advocate for you to think in terms of workflows and frameworks and how you can develop those using generative AI instead of asking the generative AI to do the work for you, looking at the data for you. But that's also changing. Yesterday's talk touched on agentic use and things like that. I personally haven't really touched on that stuff, but that may get us closer to true artificial intelligence. I don't really know. But all of that is going to be way faster than what the bureaucracy is going to move at.
Hi, in the back. Wonderful talk. I really like your framing of IA. We use it all the time in my lab for these higher level tasks that you've described. One of the things I noticed doesn't get described very often is the use of IA for lower level tasks. So like the technician persona was missing, right? One of the things that's really benefited my lab recently is using optical character recognition, which some of the language models is able to help with. And so we've actually redesigned all of our data sheets. We can scan a year's worth of data sheets in like a minute. And data entry can be a beast. And so I was wondering if you could just talk about how maybe these like lower level tasks are also being benefited by these tools.
Yeah, for sure. I didn't really want to talk about that because there's obviously a concern about these AIs replacing a lot of the potential jobs out there. And one of them is data entry. I feel like machine learning now, when it's paired with LLMs, is essentially solved. There are a lot of models out there that are very tiny. You can run it on your phone, and they will do a very good job at reading PDFs and reading handwriting and things like that. And so I think, like I said, a tool can never truly replace its user. And so if you are a user of a tool that then starts to creep onto your expertise, I think you need to evolve with that tool. I think you need to start thinking about how you can utilize that tool to increase your own capabilities. And like I said, there's a learning curve, but you can just use natural language to learn. And I think that's the beauty of these products. And so I think just be curious, even if it makes your job, your specific job, obsolete, there's other things that you can do with it, that you can build from your own knowledge. But for sure, there's a lot of things that they are capable of beyond just working at the framework level. Thanks all.
Thank you, Trinh. Thanks for those questions. All right, our second plenary. Dr. Joseph Merz is a fisheries scientist and restoration ecologist with more than 3 decades of experience leading applied research and large-scale river restoration. projects across the Western US and monitoring aquatic ecosystems and estuaries in the Western US and Europe. He's the president of and a principal scientist at Cramer Fisheries Sciences, a research associate at UC Davis and Santa Cruz, and developed a patented non-invasive aquatic sampling platform that integrates advanced sensing, video, sonar, and data science to improve monitoring and management of aquatic ecosystems.
Wow, what a great talk, Trinh. I really appreciate that. I'm going to take this to a slightly different level here. I didn't realize this was moving forward. Interesting. Okay, here we go. Okay, so I wanted to start off with fears, concerns about artificial intelligence. So of course I want to co-pilot, and I asked it to tell us a story about how machine learning was going to take over our jobs. And within 90 seconds, it came up with this cool story about, well, terrifying story about a program taking over AI, FinNet taking over monitoring. It comes up with a false story about oxygen depletion in the estuary and the oceans, governments being terrified, putting out monitoring bots to take over our jobs. And within a short period of time, we come to find out that the story is wrong, but by that time our jobs are gone. The beauty of this is it didn't make up a story where somehow it was right. It actually followed what I asked and told a story about taking over, an artificial story, which I actually think is quite interesting. But it feeds into our common fears here that AI makes decisions instead of people, results are black box that can't be trusted. But actually, today, right now, for me, for my lab, what we do, AI handles a ton of information. It helps us analyze that information, distill it, doing counting, detection, forecasting. But humans are still making the decisions and remain accountable. And what actually matters is that validation where we are driving what machine learning and artificial intelligence is doing. Human oversights for rare, high risk, or high impact cases, and I'll talk about that in a second here. The bottom line is that AI speeds work, not authority, and that really good governance matters. That's the important thing here. So, where is AI being used in the estuary today? Well, there's a ton of stuff that's happening. I mean, we all know this. We're already using artificial intelligence to augment the work that we do in very specific ways, doing spell checks and things of that nature. But we've got programs where drones are basically taking high definition images, and we're using artificial intelligence programs to analyze the images, to do habitat mapping, look for trash. We've got surveys that are being done now from aerial imagery, satellite imagery for algal, detecting harmful algal blooms, actually building models to predict when it's going to happen. Automatic fish counting, and I'll talk quite a bit about that in a second. And of course, robotic stormwater sampling is happening already in the estuary. One of my favorites is the wildlife cameras and sounds where AI is being used to survey for bird calls, for rare birds, or for wildlife. I love this stuff. There's so many cool things going on out in the estuary right now. So let's talk about some of the things that I'm most familiar with, what my lab has been working on. We'll talk about some limitations, some issues, but some of the cool things that are happening out there that we've been fortunate enough to work on. I think one of the most well-known things is taking deep learning object detectors and retraining it for looking for organisms in imagery. So think about fish passage surveys and things of that nature. And it's actually getting to be quite exciting. For instance, we use both sonar or sound imagery, and we use light imagery for monitoring fish passing through fish ladders. It's painstaking. Sitting there watching videos. I started that with East Bay Mud back in 1996, 1995, sitting there watching videos all day long. It was brutal. It was a great starting job with them, but it was rough. But the idea here is that basically we can use these Python-driven programs to search not only just for objects and blow off all the video where there's nothing there, but for instance, being able to, could you tell that's a lamprey down there? Okay, that sine wave, that curve, and the tail beat alone helps us classify that that is an adult lamprey in the ladder. Now on the flip side, sonar sucks in a fish ladder. It bounces off the walls. It's meant for big open areas. It works great in turbidity, which is the reason why it was installed at this location, but it's not great and it creates a lot of issues. Now, we're really starting to take off here. This is with East Bay Mud. I love seeing this. I could tell you a ton of stories about my dad and me thinking things through back in the day as a grad student. Taking these ideas and actually now seeing 20 years plus later, machine learning helping us not just identify species, but separating out the sexes, looking for adipose fins on salmon. But some of the problems are air bubbles in the water, bubble curtains basically can mix up the program. It gets confused. When we've got shadowing of fish, it has a hard time tracking more than one fish. When we've got precocious fish, it's very difficult to tell males from females. So what? It's not doing it all on its own. It's augmenting what we're doing. Now think about, okay, that's a stationary camera, and Kai talked about that yesterday. Bobby also talked about moving the camera through a system. Imagine pulling a trawl through the water where you start and stop and where organisms are actually picked up. Very difficult to figure that out when you have to stop and sort your organisms. This is going to keep happening to me, isn't it? So in this situation here, we not only can track individual fish out, we can have the program ignore debris, and we can actually have it track organisms as it's moving past thresholds to do counts per volume of water for us. So we can actually detect fairly fine scale where we're seeing concentrations of organisms. Zooplankton, a little more difficult. Video doesn't work great there. High definition cameras are extremely important. In this situation here, right now, we're collecting thousands of images for transects, okay? Terabytes of data. Can you imagine looking through images, trying to identify zoopes? We literally now have got it so that the program can process an individual image in about 3 seconds or less. So in a 15-minute transect with thousands of images, we can do it in 3 hours with a pretty high comparison to human identification of organisms. AI is even helping us with eDNA. So back in the day, you would have to compare your barcodes between an organism and a voucher specimen. AI is speeding this up in the laboratory very quickly. As long as you have that voucher, you can determine whether or not that organism is being detected. So water's being pulled through a filter, that filter is taken to a lab, it's being processed, okay? Really speeding up the delivery of eDNA. And the beauty of this is we can do certain things with it. It's not a fix for everything. And again, eDNA is its own issue. This is the processing of eDNA data that I'm talking about here. This is data taken from Dutch Slough Habitat Restoration Project. The size of the circles are read counts of eDNA from a given sample. Okay, so relative size is how strong the signal is. The yellow is pre-breaching of levees at this restoration site. And these are all native fish species that were detected. So we can see that even before the breaching happened, without doing any physical handling of organisms, we had detections of fish out at that location. If you let your eyes catch on to this, we can see like sculpin, where they're consistently there. and there are pulses of them, but we've got split-tailed shuck coming up and leaving. We've got salmon coming up and leaving. We can actually see seasonal pulses of organisms without actually handling them and processing that data very quickly. Moving on to fine-scale monitoring. Department of Water Resources has acquired numerous duck clubs and are managing in many different ways. This is an example of where flood up occurred to knock out Russian thistle. Water's put out on the floodplain, it's inoculating that habitat with phytoplankton, nutrients, and then you've got organisms like Russian thistle breaking down and decaying, and there's a soup out there. What happens when it comes back? So here we are with our boat moving through that plume that's coming back, and you can see the live box on the right-hand side. We can actually, with the imagery and the processing, we can see where within the plume the organisms are. So now we can overlay water quality before and within the plume. And if you look at that bottom track there, we're not only looking at organisms, but debris, for instance. Where within the plume are we getting organic material showing up, which is the black bars? The blue bars are individual fish. We can actually see that the fish are hanging out in the plume. They're not from the floodplain. They're moving into the plume to feed or actually hide from predators. I can't tell you the whole purpose behind that. I can just show you those assimilations and being able to process these data really quickly. Taken to a bigger scale, again, Bobby talked about this in the shipping channel yesterday. This is a plot of 20 miles of numerous continuous transects taken through the shipping channel using shadow imagery and then processing it with AI. Look at that track of Zoops. Isn't that friggin' cool? That's 20 miles processed with AI as opposed to people processing it. Have you seen that before? It's exciting and it actually makes the hair on the back of my head stand up how cool this is that we're able to crunch these data like this. Other things that are important here is behavioral stuff. When we do habitat restoration, putting woody debris into a channel, one of the tributaries to the estuary, what's that woody debris for? Woody debris is cool, right? We just say, oh, it's cool. It's part of a healthy ecosystem. But why? Well, if it's habitat for fish, it's going to have an effect on its behavior. How do we measure behavior? If a juvenile salmon's hanging out with woody debris, it's hiding from flow, right? It's protecting itself from current. It's dancing out into the velocity and feeding and coming back. It's energy conservation. How do we measure that? Humans, that past picture, my crew out there, what are they doing to the behavior of those fish by being there, right? It's a cool picture, but what the hell was going on there? This is a box where we're detecting movement, okay? And we can group it as the blue bar is resting. There's not a lot going on. And the red bar is agitation, is movement. If you look in that right-hand corner there, you see a little pink thing there, that's actually a tethered hatchery Chinook salmon at a location where we're going to put woody debris. Now, watch resting, and the red is predation, a stress event. And here we've got an invasive predator coming in. You can see the process where an algorithm is helping us quantify activity at that location with a passive camera. We can move this to so many different directions, tracking fishing pressure, okay? If any of you have done creel surveys, it can be a fun thing and it can be a terrifying thing, right? Going out, interacting with boats, interacting with anglers who are either happy or not happy, they're tired, they're stressed, whatever, right? Being able to set up cameras to actually track boats is extremely important. Each one of these boats is heading out to go fishing. How do we know whether it's going out or coming in? Well, boats have a port light and a starboard light and a rear end light. The left side of the boat has a red light, the right side of the boat has a green light, and there's a white light on the back end, so you know if the boats are moving this way, that way, away from you, or coming to you, or if it's stationary, it's a channel marker that isn't a boat. So we can process a lot of information without being invasive, without getting into people's personal stuff, tracking angling pressure. Remote sensing for habitat. I think most people know about this. Okay, we can use drones, we can use satellite imagery, aerial imagery to actually take high definition cameras. The beauty of AI is the ability to automate telling water from habitat, or from terrestrial habitat, mud flats from vegetation. It can do a beautiful job. And if you've ever tromped out in the field to do wetland delineation in tidal mud flats, it's a lot of work, right? So you can really do some great work here. You can standardize things. And just like everything else, I've been trying to go, I haven't been trying to, I've been glossing over a few things here. I've been trying to put down the risk on everything. One of the things about this is that AI could do a beautiful job, come up with some really neat maps of things. But if you don't pay attention, you can actually see that in many cases, it can gloss over or miss things. So humans still need to be an important part of that process. Evaluating habitat comes in many different forms. So for instance, when we do habitat restoration for spawning or rearing habitat for salmonids, it's not just, oh, that's a riffle, that's a pool. There are also features within those sites. Woody debris, again, extremely important. How much woody debris? It takes a lot to go out and take measurements of wood or substrate, particle sizes. In this case here, we're taking images of substrate. We've got a template up there. I used to use my foot all the time, and I keep my foot in there because I know the size of my shoe, and I can actually, that's the way I used to do it. We can use templates now, and now we can use machine learning to associating, using the Pythagorean theorem, associating the size of particles, the X and Y coordinates of the particles, to the size of the template to classify these rocks. That's a beautiful piece of artwork. I've got it up in my office, but that is all color-coded by the process to classify substrate. Substrate, if a female steelhead, for instance, uses 10% of her body length, and we know the size of the rock, we can then say whether or not this is actually spawning substrate, or it's too big, or it's too small. If we've got macrovertebrate associations with rock size, we can model out whether or not we're going to have an effect on the benthos from the rocks that we place in habitat restoration. Even simple programs. How many of you go out and sample and you got a fish finder on your boat, an old Lowrance? That Lowrance collects a lot of really cool data, and we can come up with great algorithms to mask out noise from what's actually happening with the data. So for instance, this is a plot from predicted submerged aquatic vegetation from our fish finder on our boat. If we've got the X and Y coordinate and the time, we now associate that with our images. We now have a map of submerged aquatic vegetation that goes along with our imagery out at the site. Think about how long that would take you to do that manually versus having this process set up for you to post-process a card, the data on a card from your fish finder. So risks and limits of using AI in resource management. AI can fail quietly when conditions change. Think about weather mapping right now with climate change and how difficult it is. How many of you went, it was supposed to rain yesterday, or it was supposed to be, right? I mean, it's difficult. Climate is changing. Our models, we've got to keep up with it, right? AI performs worse where mistakes matter most. Rare species, for instance, if you don't have vouchers, you can't train your AI. Okay, you need, I think you saw yesterday, for you, those who were here, hundreds, thousands of images to separate males from females, salmon, right? Imagine trying to look for delta smelt out in the environment. and how many voucher photos you have for doing that. Data and sensor determine reliability. So things like fouling, bubbles. If you've ever had algae float on front of your sensor and your sensor uses green light waves to detect chlorophyll A, you get a false positive with that, right? Over automation creates false confidence. As you get things cleaned up and really moving forward, you get yourself comfortable sitting in the passenger seat, falling asleep with not paying attention to the driver, right? AI lacks local and cultural context. This is not to replace humans. There is cultural knowledge. There is local scientific knowledge that has to be driving this system. You can't forget about that. Where it can win. We can see connections across regions, combine regional eDNA, for instance, and remote sensing to track species movement and ecosystem connectivity. Think about invasive species. Think about the golden mussel and its movement and how quickly it's moving out. The ability to process eDNA and track the movement as opposed to going out and looking for those organisms. Testing decisions before acting. I love this. We do this all the time when we're doing habitat restoration. How do we know that the design for a new gravel bar or a side channel or a seasonal inundated channel is going to activate when it's supposed to, or how long it's going to happen, and whether or not it meets habitat suitability criteria for our target organisms? Doing 2D modeling is a great example of that. We can do what ifs with it. And with new programming now, if you know your particle sizes, you can make estimates of scour, sediment deposition. You can really make strong predictions of how well habitat restoration is going to work before you actually implement habitat restoration. Comparing results across projects, shared open AI pipelines, enabling consistent methods, defensible comparisons across agencies and regions, right? So the idea here is that we all get comfortable with it and we all utilize it in the same way so that we can compare across large scales. What does the peer-reviewed literature say? AI supports narrow tasks, managers keep authority, biggest technical risk is domain shift. By the way, I used AI to search for all these papers. Biggest technical risk is domain shift, so performance drops across seasons, habitats, or sensors. That gets into that idea about trying to take a model from here and putting it somewhere else. Human in the loop is the recommended model, especially for rare or regulated cases, and adoption is bottlenecked by governance and trust, not autonomy. We didn't even talk before our presentations. I'm really glad things are so well connected here. So what managers can do now: start small, pilot AI on 1 or 2 clear management questions, fund oversight, budget for validation and human review, use local knowledge, build data governance and local expertise into AI workflows, use your local people, your local knowledge, your experts to design your studies. Don't ask AI to design your study for you. You can ask it to give you complementary ideas, but you need your experts doing that, right? Weigh costs, ensure benefits, justify the computing and the energy use. It's going to cost a lot for computers to crunch large data sets, right? You got to think about that. You got to justify what you're doing. So the takeaways: AI is already useful for counts, compliance, and early warning. When applied carefully, validation and context matter. Humans stay in the loop for rare species, edge cases, and decisions. Start small, scale up, plan. The bottom line is AI is a tool, not a replacement. So part 1 was that story that I made up. Part 2, the reality. There's a lot of really cool things that are going on with AI. I really see things like dark fleets, big ships that are out harvesting the ocean, doing it illegally. Those things are going to be a thing of the past relatively soon. In the same timeline as that story that I had Copilot make up. Test management actions before acting. We already talked about the digital twins, like modeling habitat restoration. Faster species detection. I can guarantee you eDNA is going to be done with hand tools, computers out in the field within the next decade. No problem. Not taking months or weeks or a couple of days to get data back, but getting it back relatively quickly. AI handles routine tasks, but humans manage decisions. I think that's going to be consistent through time. Okay. AI doesn't replace scientists, shifts effort from intense sampling to data processing to better, faster. It relieves us from doing more mundane tasks to do the cool stuff that we want to do. And with that, if I didn't have all these cool people and these co-workers and collaborators and supporters, I wouldn't be here talking to you. So I want to say thank you to all of them. And I also want to say thank you for giving me this opportunity to speak.
We do have about 5 minutes for questions.
AI slop has become a major issue in a lot of areas. Is there any indication that this should be an issue that we may be concerned about in the sciences with studies created, produced by AI that aren't valid science?
Oh, definitely. Anybody that is relying on AI to do their work for them, they should be called out. That's inappropriate use of the tool. Let's put it that way. Yes. I also want to emphasize too, you should never be using AI all by itself. Just like not going out and sampling with just one tool, you should be looking at things in several different angles and ways. That should never stop.
So Bryan Nguyen was wondering if you could elaborate more on your use of AI specifically with the eDNA work and the meta barcoding. You mentioned voucher specimens. Are you using Gen AI for comparisons of voucher specimen to find sequences?
Yes, it's definitely being used to find sequences. So it's basically comparing sequences to sequences. You still have to use the human testing of it. You don't just rely on it on its own. It helps you find things that look similar. Make long story short, it's just like using spot pattern analysis or human face recognition, and then it's validated by geneticists. Yes. It's a little outside of my wheelhouse. It's not what I do. It's what the genetics lab does. And I will very clearly say that that is not my expertise.
Yes, thanks for your talk. I was interested in one of your advantages that you were proposing, which would be a shared kind of data. And I was just wondering if you could say a little bit more how you envision perhaps who would be managing a shared data set for images. Say we're trying to put together an image data library for species in the Bay Delta. Is that something that you see we just rely on the large data Googles to do it? Or is it something that we could do like across agency, a more local kind of database, more similar to the agent yesterday?
You know, that is a great question. Can you hear me like this? I feel like I'm echoing. That's a great question, whether or not you're talking about AI or not. Okay, I used to be part of a acoustic tagging consortium in the Central Valley. I was just basically collecting data on tags. And we had concerns all the time about people coming in and taking data from grad students for their own work, right? That's a policy that has almost nothing to do with AI. It has everything to do with the ownership, maintenance, and protection of data, whether it's someone's intellectual property or it is someone else who's paid for that entity to collect that information.
Well, I guess what I was saying is if our goal is to try to make sure we have enough image information to identify some of these rare species, or perhaps, transfer learning from higher resolution to lower resolution. It could you envision trying to put together a data, like an image-based database for, specifically I'm thinking of classification.
Yeah,
Cross-agency or.
definitely.
Like that.
And there are already image databases that are out there that are privately owned, publicly owned. But yes, as this comes online, resource agencies, I would see them actually having voucher images that have been certified that this is a female Chinook salmon that is an early stage. She's still green, estimated to be a 3-year-old fish. Yes, definitely, definitely. Yep.
I think that's all we have time for right now. Thank you so much.
You bet.
All right, excellent speakers. Thank you so much. Thank you for those questions too. We're gonna take a 15-minute break. Please be back at 9:50. Good morning, Florian.
You're all set. Everything's loaded. I just need to open them up and we'll be all set.
All right, if everybody could start making their way to their seats, we're about to get started.
Good morning, everyone, and welcome to the session 8, Delta Smelt or Longfin Smelt Part 1. So my name is Florian Mauduit. I'm from UC Davis, and I'll be moderating this session. So in this Part 1, we have 3 presentations scheduled for the next hour, and I'll start with a talk on scalable supplementation strategies for Delta Smelt recovery. This will be followed by Sebastian Gonzales, who will present work on acoustic telemetry in Delta Smelt, and then Claudia Macfarlane, who will discuss spatial and temporal changes in Wakasagi abundance and distribution. So in my talk, I'll present results from several collaborative studies conducted with DWR and MWD. And we explored different approaches to diversify supplementation strategies for Delta Smelt recovery. So why explore alternative supplementation strategies? As you all know, current supplementation relies on hatchery production at FCCL, which currently produces about 125,000 fish annually, with plans to increase production to 200,000 by next year and potentially 500,000 by 2030. At the same time, recapture rates remain very low, and recent analysis even suggests that releases have not produced detectable population level effects. So together, this highlights the need to explore alternative approaches that can both expand supplementation capacity and increase fish persistence after release. So it also needs to remain cost-effective, low labor, and scalable. So to address both production capacity and post-release persistence, we explored 2 complementary approaches. The first approach focuses on the river, where we explored rearing earlier life stages, specifically embryo and larvae, to diversify supplementation. The second approach focuses on impoundment, which could provide a parallel rearing system outside the hatchery while allowing fish to acclimate to more natural conditions before release. So let's start with the river strategy, where we are testing whether Delta Smelt can be released at earlier life stages. So I'll come back to the impoundment side of our work in a few minutes. So one of the first challenges we faced was that Delta Smelt larvae between 1 and 150 days post-hatch do not transport well. Like they are extremely sensitive during that period and survival drops like quickly with handling and movement. So we asked whether we could avoid transporting larvae altogether. And because delta smelt are naturally sticky, we tested whether we could just like fertilize eggs onto a substrate in the lab and deploy that substrate in the river to allow embryos to develop and hatch in place. So this idea was partly inspired by previous work on Wakasagi hatching frame. But in our trials, fertilization success was low and inconsistent. And like for the Wakasagi hatching framework, fungal growth quickly spread across the substrate, leading to very limited hatching success. So we decided to set this approach aside and explore a different strategy. We tried to hatch embryos directly inside river enclosures. So to do that, we used a river enclosure system that was originally developed to rear delta smelt from larvae to subadults. And you can see these enclosures like on the top pictures. And they're like a nested design with multiple mesh sizes, allowing water to circulate while keeping embryos contained and reducing flow velocities so newly hatched larvae are not forced against the mesh. And inside the enclosures, we placed the embryo in a 300 micron mesh basket that on the bottom left picture. And we suspended this mesh basket in the middle of the water column so that prevents the embryos from sinking into organic matter, and that also allows the newly hatched larvae to swim upward and use the full enclosure space. So it's important to note that with few simple modifications, like adding a releasable bottom, this system could also be adapted for early life stage release experiments. So to test this approach, we conducted 3 field deployments last year during April to end of April to end of May, using the river enclosures at the Rio Vista Army base. And so in the first deployment, embryos hatched successfully, confirming that hatching in the enclosures was technically feasible. In the second deployment, we observed moderate survival with about 13% of fish still alive after 1 week. And in the third deployment, however, the survival dropped dramatically, and we observed near total mortality. So across these 3 trials, we noticed a clear pattern. The post-hatch survival declined as temperature increased. So it's important to understand that initially we scheduled this deployment in April to do our experiments when the river was at 16 degrees to match the temperature of the river with the temperature used at FCCL to rear these embryos. So our issue was that the temperature was at 16 degrees when we started on April 22. But by the end of May, when we finished, the temperature had increased to 21 degrees, which likely contributed to the poor survival we observed. So this year, we actually adjusted our strategy and asked FCCL to rear these embryos at 12 degrees and shifted deployments earlier in the season when river temperatures are lower. So those trials are currently ongoing, so I don't have full results yet, but our initial observations suggest that higher hatching success and improved survival during the first few days post-hatch under cooler conditions. So now I'd like to shift to the second strategy we are exploring, which uses impoundment as a parallel rearing system. So the idea here is to use ponds as a parallel culture system outside the hatchery. So this could help alleviate space constraint at FCCL, reduce labor demands, and ultimately increase overall production capacity. So at the same time, impoundments may serve as a traditional wilding step between captivity and the wild. So by exposing fish to more natural conditions before release, we hope to improve their ecological fitness and potentially enhance post-release survival. So our first question was actually, can we raise delta smelt in impoundment? So let me walk you through the main finding from these two impoundment trials. Starting with the top row, which shows results from the first deployments. So on the left, you have the survival, and you can see that we had like over 95%. Sorry, I skipped a slide. You'll get lost. So to test this impoundment approach, we conducted like 2 field trials in October and May of last year. And that work was supported by Metropolitan Water District. And so we used their impoundments on Bolden Island. So you can see the location of the 2 impoundments we used on the map there. And we used like one pond that we named West and another one that we named East based on their respective locations. And so we had like floating mesh enclosures in these impoundments, and we used them to expose fish for a month or like up to 3 months to natural temperature, ambient light cycles, and natural food availability. So it's important to understand that we never fed the fish during these trials. And so the goal again was to evaluate whether this semi-natural system could support survival and growth, and if they could serve as a scalable, lower labor alternative to traditional hatchery rearing settings. Now we are back to the results. So again, you can see the survival during the first deployment on the top left, and we had over like 95% of survival after 1 month of deployment in both the east and west pond. On the top right, you can see the growth. So in the east impoundment, fish grew by almost 40% of their initial body mass. However, in the west pond, like we have a growth of about 0%, meaning that the fish mass didn't change during the deployment. The bottom figures represent the survival and growth during the second deployments that lasted 13 weeks. So we did 2 assessments, one after 6 weeks and one at the end of the 13 weeks period. And you can see that the survival was over 80% in both impoundments after 6 weeks, but it declined a bit, especially in the west impoundment after 13 weeks. And it was like because of postponing mortality. And again, you can see that the growth in these ponds was positive, meaning that the fish gained weight during the 13 months deployment, suggesting that the fish were able to use the natural food that was available. So after testing impoundment enclosures, we saw that fish could survive and grow well under these semi-natural conditions. So the next question was whether we could simplify the system and scale it further by removing the cages entirely. So we tested whether free-swimming delta smelt could be reared directly in small pond. And so this study was conducted with the Metropolitan Water District this fall and focused on 2 main questions. Can this pond support survival of free-swimming fish? And can we reliably recover them afterwards? So we conducted 3 trials, refining the deployments and harvest methods each time. So here I'll show you a video of one of our deployments. So at the start, we are at FCCL picking up fish for transport. So you can see our transport trailer, which we use to move fish from the hatchery to the field site. So we net the fish from the tank and count them into buckets to keep track of the number being deployed. So for our study, it was 3,000. The fish are then poured into the transport trailer. And once everything is loaded, we close the lid and transport the fish to the impoundment site. So here we arrive at the pond where the release will take place. So before releasing the fish, we check their condition inside the trailer and then open the valve of the trailer connected to a hose that runs directly into the pond. And here you can see the smelt just like being released into their impoundment. So 1 week later, we returned to that pond to harvest the fish. So to begin the harvest, we drained the pond down to about 2 feet of water, which helps concentrate the fish. So first, we use a seine net to guide the fish towards a deeper concrete box for collection, where they can be more easily recovered. Once the fish are concentrated there, we use the FCCL fish pump to transfer them out of the pond. They are recovered into a stock tank, and from there they are like moved using pitchers into the transport trailer, and we counted them to keep track of how many fish we recovered. And so once we estimate that most of the fish have been collected, we transport them to another nearby pond where they are released into a 20-foot recovery enclosures that allows us to monitor their post-harvest condition and recovery and make sure that our harvest process is not overly stressful for the fish. So across all deployments, recovery rates were very high, between 90 and 95%, meaning we were able to recover most of the fish from the ponds. So of those fish, the vast majority were alive at harvest, with between 88 and 94%, indicating that the rearing and harvest process themselves cause relatively little mortality. In the second deployment, where we monitored the fish like for 1 week post-harvest, we saw like very little mortality, again, with 80% of the fish we initially deployed still alive, suggesting that the process is not overly stressful. So overall, these results indicate that free swimming pond rearing combined with this harvest method can achieve high recovery while maintaining good fish condition, suggesting that free swimming impoundment could support delta smelt supplementation efforts. So we tried to run the numbers, and in terms of scaling, cages can hold roughly 1,000 to 2,000 fish each, and multiple cages can be deployed within a pond. At the same time, free swimming pond could support 5,000 to 10,000 fish per pond, which means impoundment could scale to tens or even hundreds of thousands of fish. So this could help support the program production target of around 200,000 fish by next year and 500,000 by 2030. And so, importantly, I believe that this concept is already moving towards implementation, with the US Fish and Wildlife Service starting construction of rearing pond on Balding Island this spring or summer. So to conclude, we explored two complementary paths towards strengthening delta smelt supplementation. The first focuses on early life stage releases in the river. And so our trials showed that embryos can hatch successfully in river enclosures. Also, success appears to depend strongly on seasonal conditions and particularly cooler temperatures. The second approach used impoundment as a parallel rearing system where fish can grow under semi-natural conditions while reducing pressure on hatchery space and labor. So these systems also offer strong scaling potential using either cages or free swimming ponds. So together, these strategies suggest that diversifying supplementation could increase production capacity while potentially improving the ecological readiness of fish before release, which we are currently testing in another project. So I'd like to thank the team at FCCL and my lab mates from the Fungi Lab who made this work possible, as well as our partners and funders, including the Metropolitan Water District, DWR, and the state water contractors. Thank you. I believe that I don't have time for questions. So hit me up after if you want. Our next speaker is Sebastian Gonzales from UC Davis.
Hello, everyone. Thank you all for being here. Yeah, my name is Sebastian Gonzales. I'm a PhD student in the Fish Conservation Physiology Lab at UC Davis and a 2025 Delta Science Fellow. Our team has been working to assess the feasibility of acoustic telemetry in Delta Smelt using a newly miniaturized acoustic transmitter, and today I'm really excited to share an update on our findings after more than 2 years of progress. So to outline what we'll be covering today, I'll begin by introducing acoustic telemetry and its relevance to Delta Smelt. I'll then review some of the key conclusions from the early stages of this project before moving into our more recent findings from the past year. And then I'll conclude by quickly highlighting some ongoing and upcoming work. And my hope is that you leave this with an appreciation for the progress that we've made, but also for some of the challenges that practitioners and researchers are going to face in implementing acoustic telemetry on these fish. So acoustic telemetry is a very well-established technology used for tracking fish. It relies on two primary components, first an acoustic transmitter or a tag and an acoustic receiver. The transmitter is a small battery-powered device that's usually surgically implanted within the body cavity of whatever fish that we want to track. And as the fish moves, that tag emits a unique acoustic code that can be picked up or heard by acoustic receivers. So each time a receiver detects that unique tag code, it records that event with a timestamp. And then that data from tagged fish can help us understand movement patterns from the wider untagged population. But applying that data to the wider untagged population bakes in the assumption that tagged individuals are behaving similarly to their untagged counterparts. So verifying that assumption is a crucial part in developing these new techniques for a new species. So being a species on the brink of extinction, successfully using acoustic telemetry to gather location and movement data on Delta Smelt could provide crucial insights in helping us work towards the conservation of these fish. Specifically, telemetry can help us understand how native fish like Delta Smelt are using restored habitats, what the effects are of large-scale water management practices on native fish like Delta Smelt, and also help inform supplemental release strategies as we work to recover this population in the Delta. But unfortunately, acoustic telemetry has long been unfeasible for Delta Smelt due to the relatively large size of previous acoustic transmitter models. Past attempts to tag Delta Smelt with these devices were deemed unsuccessful because of the negative impacts of tagging surgery on fish health. But that work also suggested that tagging might be possible should smaller acoustic transmitter models be developed. Which brings us to the shad tag, a miniaturized acoustic transmitter from the Pacific Northwest National Lab weighing just 0.05 grams. And the development of this tag, this new technology, has allowed us to re-examine the feasibility of applying acoustic telemetry to this species. So next I'm going to review some of the key strides that we made in the first year of this project. But while I can't cover every component in detail, I do want to give an overview of the shad tag's sort of general performance in Smelt and highlight several methods refinements that we made to help us improve post-surgical survival. And then also use those learnings to set the stage for some of the work that we did in 2025. So we began this process several years ago, developing acoustic tagging methods for Delta Smelt by adapting salmon tagging protocols, which our team had, was already very intimately familiar with. So alongside several hypothesis-driven experiments, which I'll go into more in a moment, we also made iterative improvements to our tagging procedures and handling protocols. And over time, these refinements steadily improved survival while moving us kind of further and further away from the salmonid-focused methods that we began with. So just to provide a few examples pictured on the screen, we introduced specialized nets that keep water around the fish and reduce abrasion. We developed custom surgical boards that allow the fish to remain nearly fully submerged during surgery. And we took steps to reduce surgical time as much as possible, such that our surgeries at this point only last about 20 seconds. And these iterative changes have led to measurable improvements in post-surgical survival across our first four experiments in 2023 and 2024. So this figure here shows survival of 4 different tagged groups of delta smelt that were tagged with similar methods, again, in each of our first 4 experiments. So these fish were not tagged concurrently, but they were tagged with comparable methods. An important note here is that survival in this figure and throughout the rest of this presentation will be presented as a percentage of untagged control groups. And so by expressing tagging survival, post-tag survival in this way as a relative percentage of untagged controls, it allows us to isolate the negative effects of the tagging procedure, which is what our interest and focus is on here. So looking at this data, looking at these results, you can see that the relative survival of our tag fish improved by about 20% throughout those first experiments, thanks to the adjustments I just referenced. But in addition to those somewhat minor but critical handling changes I discussed, each experiment also addressed a specific research question. So these experiments allowed us to identify an optimal anesthetic concentration for tagging these fish. We found that smelt recovered better from surgery at cooler temperatures relative to warmer temperatures. Across several physiological and behavioral assays, we observed no sublethal effects of tagging when using our optimal methods. And finally, we worked to pinpoint the best anatomical location for surgical tag implantation within the fish's body cavity. But I'm going to expand on that more here. So as I mentioned, one of our experimental objectives was to identify an optimal incision and tag insertion location on these fish. And to get at this, we tested 2 incision locations. The first, which I'll call the lateral incision, was a small vertical cut kind of just below the lateral line of the fish, sort of in the rib cage. And the second, which I'll call a ventral incision, was a cut in the ventral side or the belly of the fish. The lateral incision has been shown to be highly successful in other sensitive fishes with similar body shapes to our delta smelt, but the ventral incision is common practice in salmonids, and again, the method that our team was kind of most comfortable with coming in. But when we tested how our fish recovered from tagging surgery with each of these methods, we ran into a frustrating dynamic in which we saw higher survival in fish tagged with the ventral incision in the belly, but we also observed much higher rates of tag shedding in those fish, meaning that the tag was expelled from the body cavity through the incision opening while the fish was still alive. So since acoustic telemetry relies on live fish bearing functional acoustic transmitters in order to gather data, our focus is on these trackable fish, not just post-surgical survivors. So in other words, if a fish survives tagging surgery, but then sheds its tag a few days later, it's essentially useless to us from a research perspective. So with that in mind, the number of trackable fish between these 2 groups was nearly identical due to this survival versus tag shedding dynamic. And then one additional caveat to this, or additional sort of note, swimming performance assessments also showed that there was a minor impairment in swimming ability to fish that were given the ventral incision, but not for those with the lateral incision. So to summarize all that again, using the lateral incision, the one through the rib cage, we observed lower survival, but 0 tag shedding and no adverse effects on swimming performance. Using the ventral incision, we observed higher survival, but also much higher rates of tag shedding and a minor adverse effect on swimming performance. So based on those observations, we were leaning towards the lateral incision being like the optimal method for tagging these fish, but we had one other avenue we wanted to pursue before feeling confident in that, which was testing the use of tissue adhesive to close incisions as our first experiment of 2025. So sutures are the standard method for closing incisions in many other fishes, primarily salmonids, in tagging surgeries, but the small size and delicate nature of delta smelt tissue makes that completely impossible on these fish. So up to this point, we had been leaving incisions open after surgery, which naturally increases the risk of tag shedding, particularly with those ventral belly incisions. So our hope was that using this tissue adhesive as a non-invasive way of closing incisions would prevent tag shedding while also maintaining that elevated survival with the ventral incision. So we designed a simple experiment to test the effectiveness of tissue adhesive with 4 different experimental groups. One group would receive a lateral incision, would get tagged with a lateral incision and no adhesive. One group would get tagged with a ventral incision and no adhesive. And then one group would receive a ventral incision with a small amount of tissue adhesive to close the incision and hopefully seal in the tag. And then of course we had an untagged control group as the fourth. But to our surprise, fish that received this tissue adhesive had a dramatic reduction in post-surgical survival compared to fish that didn't get the tissue adhesive. So the figure here shows the percentage of trackable fish remaining over the 30-day experimental period. And again, this means that trackable fish means that fish were alive and retained their tags and presented as relative to our untagged control group. And as you can see, the fish that got the adhesive, shown by that red survival curve on the bottom, were clearly more negatively impacted by this procedure. And what's more, not only did the tissue adhesive have a negative impact on survival, it also completely failed to reduce tag shedding. So although we're not certain exactly what the cause of that impact was, we think it likely had something to do with the increased time associated with applying the tissue adhesive, or the fact that we had to dry the fish's tissue in order to get the adhesive to adhere to the fish, and that probably impacted recovery or inhibited their ability to recover in some way. So all in all, this made us confident that the tissue adhesive wasn't an option, and that the lateral incision remained the optimal approach for tagging these fish in future experiments. Which brings us to the next experiment we conducted in 2025, exploring elevated dissolved oxygen and elevated salinity as a way to recover fish from tagging surgery. Both of these water quality conditions are known to give physiological benefits to fish under stress, at least when exposed to them for short periods. And both of these are also often used to improve survival in delta smelt when they're being transported between facilities or to release sites. So we designed an experiment here to test the potential benefits of each of these conditions on surgical recovery with 6 treatment groups. Our treatments were divided into 2 kind of broad subgroups, freshwater groups and saltwater groups. And then within each of those freshwater group and saltwater group, we had an untagged control group, a group that would get tagged under normal dissolved oxygen condition, and a group that would get tagged and then exposed to supersaturated dissolved oxygen for a short period, a 60-minute period. So the survival curves here represent the 4 tagged groups within this experiment. The freshwater tagged groups are presented relative to their freshwater control, and the saltwater tagged groups are presented relative to their saltwater controls. So as you can see, there is a clear benefit from the elevated salinity, which nearly eliminated the acute mortality that we observed in that first 5 to 7 days post-surgery in the freshwater groups. There was no observed effect from elevated dissolved oxygen in this experiment, but the 94% relative survival that we saw in that top saltwater group, the dark green bar, was our highest post-surgical survival to date. And that brings us to our final question that we explored in 2025, which was the importance of surgeon skill and experience in tagging success. So up to this point, the same 2 surgeons had tagged every single fish in all of our experiments from 2023 through 2025, totaling well over 1,000 tagged delta smelt for each of them. So although we'd come a long way in refining our methods, it was still unclear whether a less experienced surgeon could walk in and achieve comparable success just simply by following these protocols that we developed. So we tested this by having our 2 experienced surgeons tag a batch of fish alongside 2 less experienced surgeons. These less experienced surgeons had handled fish often. They were both research staff members within our lab and each had some level of acoustic tagging experience on salmonids, but they had no experience on acoustic tagging delta smelt outside of the 10 practice fish that they had kind of as a warm-up on the experiment, or prior to this experiment on the same day. So this figure here shows survival relative to untagged controls again, with the 2 experienced surgeons grouped together and the 2 inexperienced surgeons grouped together as the green line. And you can see a clear difference in survival between these 2 groups, with fish tagged by our experienced surgeons surviving roughly at a 15% higher rate, highlighting the value of both the explicit and the tacit knowledge that these surgeons had accumulated over their thousands of surgeries. And it shows that simply providing these methods to new practitioners isn't going to be enough. Tagging these fish requires a substantial amount of training and hands-on experience before these techniques can be implemented successfully. So I'm just going to flash these kind of final results from 2025 up here again to summarize. Tissue adhesive is not a viable option for these fish. Elevated salinity boosts recovery or boosts survival post-surgery, and surgeon experience is extremely critical in success. Which brings me to our ongoing and upcoming work. Quickly here, bringing, so delta smelt being a primarily annual species, tagging sexually mature adults is unavoidable. So we've been investigating how tagging success may vary across different stages of gonadal maturation, pre-spawn, active spawn, or post-spawn. We're also looking into how fish respond to an additional stressor, namely transport, potentially to a release site immediately following surgery. And we're also looking at how fish respond to surgery in a more uncontrolled non-hatchery environment. And then lastly, our team at ICF, along with collaborators at US Fish and Wildlife, have been heading an effort to establish range and detection efficiency parameters for the shad tag in preparation for tagging and tracking fish in the wild, hopefully in the coming years. And with that, I'll just say thank you to our funding sources and the many collaborators we have on this project. It's taken a giant team of incredible people to make this possible, and so thank you very much.
I think we have time for a couple questions.
Yeah, it was a great talk, really cool study. It's gonna be really valuable. I was curious if you can kind of go through all the steps that the inexperienced handlers were doing, and which of those do you think might have been the ones that were resulting in that decrease in survival?
You want me to walk through the entire tagging procedure? It only takes 20 seconds, so yeah. The procedure basically goes, we net a fish out with our specialized nets from a holding container and drop them into our anesthetic bucket. They're set there for a consistent period of time. We've come down on 90 seconds. That's the time that these fish stay in their anesthetic. They come out, they go on a surgery board, get an incision, tag insertion, and then get put into a recovery bucket. So where exactly the difference between our experienced and inexperienced taggers comes in, my guess is probably that one moment where they're physically making contact with the fish, right? So the amount of pressure that they're applying when they're making that incision, maybe how long their incision is, how deep they go with their cut to allow the tag to go in. That's my guess, where the physiological consequences can be kind of, coming from, but.
Yeah, that makes a lot of sense. Quick follow-up. So I'm just thinking, like, could it be the handling time of like netting and all that, or the handling roughness? This is something I train my staff on when we're dealing with longfin smelt. So I'm just wondering, could it be that, or could it also just be how long it takes for them to do it? Like, did you time them in terms of how long they're taking versus the trained staff?
Yes, and there was a small difference in surgery time between our experienced and inexperienced taggers or surgeons. All the netting and stuff beforehand is done by a separate fish handler. And so the surgeon is just sitting kind of in front of the surgery block. So all that stuff that happens before could play a role if it was different people doing that, but for this experiment at least, we just had one person who wasn't a surgeon.
I have a follow-up question, actually. How many fish do you think someone needs to tag, like to bridge that gap and become like an experienced tagger?
I have absolutely no idea. Many, I think. I mean, again, fortunately, again, these surgeries are fast, but these fish are also extremely limited. And so one thing I think that we can do is use, other species potentially as a proxy to get, practice reps in with these methods, but I have no way to provide a specific number, how many reps you need before you can be considered an expert.
Sorry, we don't have time for other questions. Our next speaker is Claudia Macfarlane.
Thank you. Just make sure this works. Perfect. Good morning. I'm Claudia Macfarlane, a data manager for the Enhanced Delta Smelt Monitoring Program, or EDSM. Welcome to my walk talk. We will be looking at changes in Wakasaki abundance and distribution. This work was put together by myself and Evan Carson. And just quickly before I get started, I want to give a quick thank you to everyone on the EDSM program and the crew members who have spent many an hour in the shipping channel, sifting through hypomesis species, or the folks in the lab, or in the data lab, carefully entering their data. We appreciate you. So having worked on EDSM in some capacity since 2021, I have witnessed, caught, and felt the logistical impacts of the increased catch of Wakasaki. This picture is the Wakasaki catch from a single 10-minute tow in 2023. We have seen increased catch over a wide area throughout the year, most densely located in the shipping channel. There's only been one single comprehensive comparative assessment of Wakasaki and the relationship with Delta Smelt to this point, and that was put together by Davis et al. In 2022. This compiled modern and historic catch records across multiple long-term monitoring surveys, paired with otolith and diet analyses to reconstruct Wakasaki distribution and life history from 1950s through 2020 to evaluate its spatial and temporal overlap with Delta Smelt. This work was imperative to provide us the foundation to do what we are here to talk about today. As a Delta Smelt program, this work is highly relevant. There are known concerns about ecological overlap between Delta Smelt and Wakasaki, with consequences such as hybridization or competition. Therefore, understanding the changes in Wakasaki population is directly relevant as we release cultured fish across the landscape and as supplementation progresses. EDSM is a good spot to look into this because our high resolution sampling across the full range of Delta Smelt allows us to use our data to evaluate another hypomesis species with the assumption that our gear targeting Delta Smelt should similarly detect Wakasaki. So now let's take a quick look at what Davis et al. Did find, starting with a figure from their manuscript, looking at integrating catch from CDFW spring Kodiak trawl. Year is on the y-axis spanning from 2002 to 2020. And on the top, we have Wakasaki detected per tow. And on the bottom, we have Delta Smelt per tow. A key note here is the scale of the y-axis. Delta Smelt is 2 orders of magnitude larger. And as we move into 2010s, we see Delta Smelt detection decrease and Wakasaki increase relative to their own prior years. And what's interesting is we can see that Delta Smelt were predominantly caught in the shipping channel, and now we see Wakasaki slowly moving into that area over time. So the key takeaways from their paper were the Wakasaki were most, and this is for the period 2020 and before, Wakasaki were most abundant in the upper watershed, closer to the reservoir sources. There's most overlap between the two species in the northern areas. And Wakasaki was found to have a low abundance and a patchy distribution. And to few's surprise, there was large overlap in habitat use, diet growth, and diets. And there was also evidence of local recruitment by Wakasaki in the system. There are some differences though. Wakasaki are known to spawn, hatch, and rear a bit earlier than Delta Smelt. And unlike other non-natives, like Centrarchids, they show a reduced growth during warmer months. All of this led to Davis et al.'s hypothesis that the persistent low abundance that we see of Wakasaki may reflect similar vulnerability to environmental variability. So we cannot explore all of the topics covered by Davis et al., but today we will share a present-day status update of Wakasaki's abundance and distribution within years, across years, and with respect to spawning and recruitment. We will use this updated catch information to revisit the question, does environmental variability keep Wakasaki abundance low? And all of this will hopefully allow us to better understand the bearing of Wakasaki on Delta Smelt and specifically supplementation. So we only used EDSM data for this to examine hypomesis catch from the program's inception in 2016 to the present of 2025. This data includes Kodiak trawls from phase 1 and phase 3. For this work, we exclude phase 2, our 20 millimeter larval trawls, due to known challenges with morphological identification of hypomesis to species. Take a look at poster number 4, reviewing the more established morphometrics criteria in the poster hall later. While progress has been made on reliable genetic methods for species verification, that work is not complete in time for this talk. So now let's take a look at Wakasaki and Delta smelt catch from 2016 to present. Here we have the x-axis from 2016 to 2025, total catch, Wakasaki's in blue, unmarked wild origin Delta smelt are in orange, and recaptured releases are in green. And that purple line just is a visual reminder of where Davis et al. Stopped, their stopping point for data they reviewed. So we can see that before 2020, Delta smelt and Wakasaki were both caught at relatively similar lower amounts. However, after 2020, Wakasaki began to increase in total catch, where we caught almost 10,000 in 2023. Concurrently, if you can see there are little Delta smelt numbers there. They are just very low relative. And so one key note here is that Delta smelt supplementation began in 2022, and since that point, most of our Delta smelt detections are predominantly recaptured releases. So for those of you that like to standardize things, this is CPUE. I'm gonna glaze past this, but I just want to show the pattern stays the same. While effort may vary from year to year, we do not, as you can see, the relationship and the magnitude of the change stays more or less the same. So now let's take a look at just Wakasaki catch and see what we can learn about the seasonality of abundance and recruitment from our data. So for fork length frequencies, results are based on a measured subsample of total catch, where we measure up to 30 individuals for each toe when fish are available, and then count the rest. So here we have Wakasaki fork length distributions by season in 3-month bins. And the colors show alternating cohort years. So for 2017 to 2020 cohorts, we see a similar seasonal pattern year after year. That July and September group are the fish recruiting into the population for any given cohort year. You can think of it as the start of the cohort year. That October-December section is where they are growing into their spawning stock. And January to March, we see a senescing or dying out of the adults. And just to note that these are non-larval detections, so adults or juveniles during that time. So let's see how things have changed. We can see recruitment change in recent years. After 2020, there's a dramatic increase in individuals that we detect. However, the seasonal life history pattern holds despite the abundance change. We have recruitment, growth, and the senescence. So here we have the Wakasaki fork length by month in cohort years 2020 and 2025, which are representative of each sampling period. One key note here is that we see the quickness that the Wakasaki die out post-December. And there are a couple more interesting features in this talk, or in this figure. So as we can see, we have groups of 100 millimeter or plus fish. And we hypothesize that these could be second-year adults coming back, still in the system to spawn. And we know that larger fish are more gravid and can produce more and are more fecund. In the shipping channel, we have detected Wakasaki of up to 119 millimeters, which is pretty large. Another interesting fact is we see a decrease in detection in August and September, but then they pop up back up in the system in October. So we know these fish aren't dying. So what we believe is during the hottest months, they may have a behavior adaptation to avoid that heat. So they may be moving out of detectability range of our gear during those hottest periods and coming back. So now let's take a look at spatial distribution over time. So here we have 3 years, 2020, 2023, and 2025, with Wakasaki on the top and Delta Smelt on the bottom. And these are calendar years, not cohort years. So as we can see, as we move through time, we see Wakasaki dominating at high levels in the shipping channel, but also they seem to be moving into the marsh more and more as we progress through the years. One interesting note is that we see Delta Smelt similarly across the landscape, but in much lower levels. They're kind of hard to detect. And we see them also in the shipping channel and the marsh. In 2025, there's one caveat that the Delta Smelt we detected that are still orange, they are waiting on genotype to see if they're a wild origin or supplementation fish. And the scale here is unified across all the species, so they should match. So now let's take a look at seasonal abundance and how that changes from 2020 to 2025. As we can see in July and September, Wakasaki are in the shipping channel in large amounts, and also Sassoon Marsh pretty expansively. And then as we move through, they stay in the shipping channel. And then we see in January and March a large drastic reduction in Wakasaki numbers across the landscape. And as for Delta Smelt, they stay in patches. However, in January and March, we can see that they have a much broader distribution across the landscape, but still at fairly low levels. And one interesting note here is that Wakasaki are really mapping onto the areas that were once historic Delta Smelt hotspots. So the shipping channel, as well as the marsh, and almost tracking to where they use those areas at different life stages. So, not going to go over all of this, but what did we see that was consistent? We saw the similar wide distribution, located mostly in the Sacramento shipping channel. We did detect that they spawn earlier than Delta Smelt. However, they're still around, as we saw in the last figure, during January and March. So there is potential for overlap, but we believe that spawning timing may reduce that. We saw local recruitment by Wakasaki and a distributional and ecological overlap with Delta Smelt. But what has changed? So we're seeing Wakasaki in an order of magnitude greater numbers. And while this may be variable from year to year, the catch has remained high. We are seeing local recruitment in quantities and locations that are unlikely to be due to solely reservoir outflow. And we are seeing Wakasaki being seasonally abundant in Sassoon Marsh. And from all of this information, we see that they may not be as constrained by environmental variability as we once thought. They also could be employing behavioral techniques to help mitigate for stressful or unfavorable conditions that their counterpart may not be able to do. So implications. We really don't know whether Wakasaki will continue to thrive. It may still be nearing its tolerance limits. The delta is warming and there's a lot of change. So we still may be getting close. But Wakasaki has a track record for invasions worldwide and adapting to new environments. And in case of bad recruitment years, they still do have that reservoir source upstream for populations, like their own supplementation program. An important note is the sheer increased volume of hypomesis detection poses a challenge for a limited resource environment. We understand the idea is difficult, and so since 2016, EDSM actually brings back all adult and juvenile Wakasakis for lab verification under a microscope. But especially for larval fish, while we have made work on genotyping methods, and those exist, the feasibility of doing that to tens of thousands of larval fish is just not feasible. And if Wakasaki poses negative effects across the broader landscape, it would be extremely difficult to control at their current distribution and abundance. And most of that remains largely uncertain. So what's next? Targeted monitoring for Wakasaki regarding fecundity, spawning, and recruitment. As we talked about, they largely die out between January and March, but just this year in February, we found a very, very ripe Wakasaki, indicating that even though we understand these life histories and life cycles, dying out doesn't mean there's none. 1% of 10,000 is still a good amount of fish. And so understanding the incidence of hybridization, as well as the viability of those hybrids, may help us understand what's going on the landscape. Otolith or genetic research to understand the proportion of reservoir versus local origin Wakasaki and how they may differ. And getting back at, we understand that Wakasaki are able to survive through summer and persist in the shipping channel, and being able to tie that back to either thermal tolerances or different behaviors that we don't quite understand yet may be helpful. And that is all I have. Thank you all for listening.
We have time for 2 questions. I see one from Levi.
Wonderful talk. Wakasaki are interesting, and I really enjoyed working with Brittany and the team on that paper. 2 points. One, there's a pretty strong evidence that there's like tens or hundreds of thousands of Wakasaki coming into the system every year, but for whatever reason, they don't make it to the Delta. I was wondering if you can comment on the reality of that and why you think that local recruitment is the primary reason and not these subsidies, especially with Oroville failing back, was that 2017, and the huge dump of surface water that came in.
And so I'm talking about in recent years in the locality of them in the shipping channel and the kind of contained area. I do agree, and I think that's part of the reason why otolith and really understanding the production of the reservoirs and how that maybe they created the base population and they've been growing from there and really, and so who's to say? But just based on our data and where we were detecting them and the size and the timing, I would assume that there is, in addition to reservoir input, a good amount of local reproduction occurring. Thank you.
Hi, Claudia. Great talk. So my question, you talked about fecundity in future studies. So is there appetite? I know how busy people are in the field, but is there appetite for staging smelt catch in the field?
You know, it's not up to me. My appetite is very different than the people that fund everything. I believe it's possible. It would depend on the interested parties and if there could be a proven effect of their fecundity and timing with Delta smelt. There's a lot of factors playing together, and so it's, but yes, I think it's always been an interest of Evan and I's to get a better handle on the actual timing because there's a lot of speculation, circumstantial evidence. However, we haven't had a targeted study to say they start here, they move here, and this is the amount that they, or the timing. So there's a lot of gray area.
Thank you so much. We were having parallel conversations about staging recaps, so.
One last question.
You showed a plot of the size distributions in 2020 versus 2025. It looks like the more abundant recent years, the fish are smaller. Did you look at that? And do you have any idea what's going on there?
No, that is one of the interesting things that we noted. And that might be due to, yeah, actually, I don't want to comment on that. That is an interesting thing that we that we saw and we wanted to look into. And that's where genetics and otoliths and understanding how those fish may be different or be staying in one small region, how that may affect their size, because they are a lot smaller. But the ones in the, we see some fairly large Wakasaki in the shipping channel throughout the year.
Thank you.
Thank you.
Excellent. Taylor, take it away.
Hi, everyone. Welcome to the Delta or Longfin Smelt Part 2 session. Thank you for attending. Our first speaker up is Leo Polansky with the United States Fish and Wildlife Service.
Okay. I was going to try to go fast or skip, just skip to the point, but they're saying 10 minutes into your lunch, so we'll see. I'm still going to give this joke that I got off an 8-year-old, so that's still happening. Got to acknowledge DWR for funding. They definitely have some goals in mind, but they give a lot of space and encouragement to figure out how to get there, so that's nice. Essentially, I'm doing kind of a big data synthesis project, so to make that happen, I'm getting data from all over the place here, Dayflow, a lot of USGS flow stations, and I really rely on that stuff, so I just got to acknowledge that, all the monitoring program that CDFW is carrying out. I should have put our own organization because using some Chips Island things. And the organizers, they're dealing with tons of emails and all that, so thank you. The motivation is, it's a life cycle model. So we're looking at trying to understand how populations change through time. So the starting point is trawl data in situ. People are going out, catching fish, measuring the environment. A common thing and a very useful thing, I think, is doing regression type models, like we caught this fish and what was going on in the environment, maybe a regression or a GAM, that kind of stuff. Or, there's maybe over 40 years now of seasonal abundance indices as a function of X2, some sort of average X2 annual time step models. But the limitation in that framework, they offer many insights, but one limitation is how do we understand the consequences in terms of population growth, rates of change, recruitment, survival. So to do that, we're shifting down to this population dynamics modeling. And the key thing here is that at that bottom equation, there's the N of T, the abundance at time T depends on some sort of prior abundance along with covariates like captured in X. I just grabbed this life cycle diagram off of one of Lewis's papers yesterday because I realized I was going first and I was like, oh, I better have something. I don't like to talk about space that much because it makes everything harder, but it's inherently spatial. The life cycle is inherently spatial. They seem to rear in edges or in the northern part of the estuary. As they get bigger, they go into the main parts of the bay, go potentially in the ocean, or they do and they come back. At the same time, the monitoring is also pretty spatiotemporal. Most of the monitoring we have to draw on is up in the northern estuary and in the delta. Bay study is our main study that gets out of the San Pablo Bay. And until recently, a lot of our intensive early life stage monitoring really only happened in Suisun Bay and the Delta, a little bit in San Pablo Bay. So I know this graph on the right is not intended to show the temporal aspects and all that of the monitoring, but basically the monitoring programs have been expanding over the years, but still kind of geographically limited in some cases, especially given that Longfin can move early on into the San Pablo Bay. The life cycle, I'm putting this in a model. We're going to unwind the time part, and that's what this bottom table is, just to get some orientation. So we want to move to as fine a time step as possible. We went with a monthly time step. At the same time, we're trying to do incorporate a bunch of years of data. So we have basically a monthly time step, and we start by tracking the abundance in January, that the age 0, the hatching larvae. I know some hatch in December, but right now we're just going to start in January. And we track that abundance as the abundances recruit into the first few months and then survive into their age 1 class and then age 2 and spawn to create another cohort. So at each month, we basically have kind of a multivariate regression describing a survival transition or a recruitment into that particular month. The equations are up there. The recruitment one's kind of novel. Laura came up with that. Survival, it's basically got to be a number between 0 and 1, and it has some randomness and expected values controlled by covariates. Most of the novel part of the work of this stuff is all in the math and stats and not so much in the biology and the hypotheses. So, and I'm skipping all the math and stats, so hopefully that's okay. To track these abundances through time, though, that we need to use data from multiple monitoring programs, and they all basically produce an abundance estimate, something like total catch over total effort times habitat volume. There's some stratification going on and some other things, but I did want to make a shout out to Steve Slater and his group. That habitat volume piece on the factor, I pulled that from work he did, and I mean, that's a lot of work figuring out sort of estimates of water volume all through the estuary and the delta. Without that, you know, people like me get stuck because I need that to make these abundance indices the way I want them, and also to come up with standard errors of the estimates, that kind of stuff. On the bottom is roughly the monitoring programs used for each month and each age class. So one of the problems that I always have to come back to, that I never want to, but I have to, is to bring all these multiple monitoring programs together. We got this question. So here's the 8-year-old joke part. Why aren't fish good basketball players? And the answer is they're afraid of the net. So when I heard that, listening to this podcast, some kid called in, I was like, I'm going to try this one out. More technically, there's all these issues around our underestimate of how many fish there are, right? They're avoiding the net, they're slipping through the net, we're sampling where the fish are not. That's a big one with the early life stage of longfin. Then we have incorrect assumptions, you know, like we have some sort of estimate of catch density, but does that represent the whole water column, part of the water column? You know, so we make assumptions that could be right or wrong there. The way I handle this is in several ways. There's some bias adjustments related to where the monitoring programs are relative to X2. So like 20 millimeter smelt larval survey or sampling in Sassoon Bay, a little in San Pablo Bay. Lenny Grimaldo had a paper 2017-ish around sampling in uncharted waters. I took data from that to draw a curve around making adjustments of how much of the population we're missing when X2 is really low and the fish are all somewhere else. But we don't always have that kind of information. So we have these bias parameters that are part of the model that are life stage, month specific, gear specific, and then some more randomness related to, you know, every year is a little different in terms of how wrong we are, and that's that year specific randomness. So that's kind of how we link in all these different monitoring programs into observing that timeline of abundances. One other thing I wanted to, in a way, this psi parameter, this bias parameter is like a control variable within the bigger model, but it turns out to be interesting in its own right. Here, we're mostly going to think about it as a control. So just going on to results, I want to see. So there's a lot to the model, right? There's 26 survival rates, 4 recruitment rates. Each of those is a multivariate regression. So there's potentially hundreds of little stories about what covariate's important where. So I'm just going to do a couple of those. And just to know, we're fitting data from like 1990 through 2023. It's a Bayesian state-space model fit using STAN. So that's how it gets operationalized. So here's that bias parameter thing. And there's a lot of different programs and life stages and assumptions about when they're the same and when they're not. But the main thing I wanted to share here is that if you look at from left to right, the age of the fish, there's kind of a dip in the summer months. So the underestimation becomes more severe. That dip seems to happen twice. Maybe it's a little less pronounced with the otter trawl information, which is that top set of, I don't have a pointer, but it's the top yellowish green ones. So there seems to be some reflection of movement during the summer. I mean, I know that's not fully new, but maybe the newish thing is that it happens twice potentially. I'd like to see otolith data and start to understand things more specifically. Anyway, so that's the bias stuff, and I'll probably move on, but it's definitely needed as part of the model. Anything else? Well, let's move on. All right, so moving on to recruitment. There's 4 recruitment sub-processes in the model: recruitment of larval into January, into February, into March, and into April. Oh, here the box plots represent realized recruitment across those 33 years from 1991 to 2023. That's when the recruitments are happening. And generally the recruitment, per capita recruitment's kind of going up through the winter and then declines in April. Maybe that's one little story. We're going to look at a bunch of these, right? So here's, like, we want to start linking rates to habitat indices. So here's one with that first January recruitment versus delta outflow. So on the x-axis is the covariate value, in this case delta outflow. On the y is the per capita recruitment. So for the 4 different recruitments, and brace yourselves, and 4 different recruitments, each row, January, February, March, April. And I just picked out 4 predictor variables. If you squint, you can kind of see the delta outflow effect looks a little bit greater in April than it does in January. The slope of the line's a little bit steeper. I mean, we can look at these in better ways. I just wanted to show it this way. OMR, that's a sensible effect. Secchi, it's kind of reverse from what I was expecting. As the water gets clearer, that Secchi depth, recruitment actually goes up. And typically in like GAM models at the catch level, I see Longfin being more associated with turbid waters. Not sure there. Temperature, as it gets warmer, recruitment goes down. Here's the between year variation within each survival rate distribution. So each box plot represents 33 realized survival rates for a given month or stage in the life cycle. So as you go through its life cycle, survival gets better and better. It goes up and up until towards the end, it's starting to come down towards the end of the age 1 and into age 2. One thing to me that jumps out though is that the early age 0 survival rates, there's a lot of variation there. So that's maybe the chance where we have an opportunity to explain what's going on. Noting that our age 1 stuff is pretty limited because we don't have ocean monitoring, and we're working with people to try to get better ocean predictor indices for that. Anyway, right now this is what we got. Here's survival rates for the first 5, so January to Feb, Feb to March, March to April. So each row is a survival rate for 4 different predictor variables. Again, so let's just focus on the outflow line, as it's always a popular one. The delta outflow for January survival is looking pretty steep, but as you get more and more down, maybe it's hard to see, but I know because I know the numbers that the effect of outflow is decreasing through the winter into May. And also the range of values, delta outflow is decreasing too. OMR, not much effect. Secchi is a little bit the opposite of recruitment. That was so there's that tension there. I'm not sure if that's a real thing or not, that as water gets clearer, survival goes down as opposed to recruitment going up. And temperature, increased water temperature bad for fish. So putting all these together, I have growth rate, I should have written population growth rate. It's basically recruitment times survival. Because we have different sub-cohorts and, you know, it's a 2.5 year life cycle. It's not a matrix model, like you can't take an eigenvalue or something that easily to come up with long-term growth rate. Anyway, so it's here I'm gonna define it as the start of the spawning abundance in December divided by the spawning abundance 2 years prior. And the left panel is looking at population growth rates grouped by water year type in which the recruitment happened. And it's kind of telling us a story we already know, that Longfin like wet years, and you could like squint and say, well, in a wet year, population growth rate's roughly twice as good as a critical dry year if recruitment happens then. But there's a lot of variability. In fact, on the critical dry year in 2021 had the highest growth rate. I haven't picked into like what was going on there yet. On the right is trying to refine our understanding about when does outflow, it's just an example, most strongly predict a positive increase in the overall growth rate. So outflow of the recruitment year, and December to January actually looks like a little bit going down. That 97 year is interesting, but I'm not sure what's going on there. I think the take home message is something like March to May has the greatest, I mean, this is just a cartoon kind of regression line, you know, just to help people visualize the trend in each panel, which is growth rate on the Y and outflow on the X. And it kind of looks like March to April is where you get the strongest sort of increase, expected increase in overall population growth rate as a function of outflow. Again, just reconciling the tension that outflow is better the earlier on in the winter versus outflow being better earlier on for survival, but it's better later on in the winter for recruitment. So where is that balance? I think that's, you know, it's just illustrating. There's a lot of work to do on refining that. So discussion, the model is actually fitting. There's a lot of parameters in the model. It's fitting, it mostly makes sense. I didn't show lots of results around predators. Laura's got some prey indices. The idea is we got a tool to try to understand local time, space, habitat things and scale that understanding up into consequences for the population in terms of long-term trends. There's lots to do. I just saw this paper, I was stealing that life cycle diagram about how the outflow Longfin relationship is decoupled, right? So it's like you guys are publishing faster than, and I know the life cycle models develop, the life cycle understanding is developing, you know, faster than I can figure out how to bring it into the model, but do more interesting models. I think interactions with space or time and food, temperature, that kind of stuff. Still trying to get better predictors for northern anchovy, striped bass. We have them, but I'd like to think about them more. Movement's a big one. Age zero spawning. Currently, it's really hard in these kinds of statistical models to separate out the contribution of potential age zero spawners to the recruitment, because it just gets confounded with the overall recruitment. You don't know where the recruits came from, so it could be less from the age 1 and age 2 and more for the age 0 or vice versa. Some of the predictors are have a clear causal explanation. I think hopefully Nguyen, if he's still here, he's going to explain everything about wide outflow affects Longfin in an hour or so. There's a lot of math and some other things. So thank you. I guess we're behind, but now when I take these bike rides, end up out here. Now I'm looking at the Golden Gate Bridge. I'm like thinking, like, is there Longfin out there? Do I know? So that's how I ended up with this picture. But anyway, thank you.
I believe we have time for one question. First hand I saw.
Thanks for that. There's so much great research going on Longfin, and I appreciate what you said at the end, that things are rapidly unfolding because there's so many teams working on it. I was curious, from a life cycle modeling standpoint, how do you take a model like this and then reconcile it with the stuff that's coming out of Jim and Levi's lab about all the life history diversity and the fact that you might have different responses among, subpopulations?
Well, without knowing specifically the word, I'll just say the big hope, for example, would be to say like what proportion of age 0 are spawning, not just that they can, or how much back and forth movement is going on from the otolith data, not just that they move at least once. And when is that timing, right? So, so those would be two low-hanging fruit ones. The role of the South Bay in contributing to reproduction, we have little to no long-term monitoring there. That's another question. Can we hardwire that in? So that's generally how I would approach it. Yeah.
Thank you. Okay, our next speaker is Morgan Gilbert with the California Department of Fish and Wildlife. Thanks.
Hey, how's it going, y'all? Let's see how the microphone picks me up. Good morning. It's great to be here with all of you today. Interesting. There it goes. I'm very excited to be telling you about the Larval Entrainment Survey, or LES, how it's developed over the last 5 years, and where we're heading here in 2026 and beyond. Before I get into all of that, however, I want to take a moment to thank our collaborators, specifically the Native Fish Unit, the Longfin Smelt Technical Team, CDFW Water Branch, and the Department of Water Resources. I also want to thank the many people listed here, and doubtless many more, who have contributed either to the design of this project or its execution. We couldn't have done this without you. As a project, LES runs out of the Fish Facilities and Entrainment Unit out of CDFW's Stockton office. This project began as the Larval Entrainment Pilot Survey, or LEPS, back in 2022. And at some point, we decided to drop the pilot from that title. So I went from being a leper to a lesser. But we continued in that original pilot spirit by taking an adaptive approach to reaching our study goal, which is to provide quantitative estimates of longfin and delta smelt abundance in areas at risk of entrainment. Now, judging by the number of people who laughed at that extremely tired joke that I think I've told every year that I've presented here, some background is in order. Entrainment is the advective diversion of fishes caused by the operation of water extraction facilities in the South Delta. Pumping activities there can reverse flows, causing fish to be drawn into unfavorable habitats or exposing them to other sources of mortality. Well, the first thing that you might think of when it comes to entrainment is direct entrainment, where fish are drawn into the extraction facilities. The broader risk that entrainment presents is in its indirect effect on the distribution of fish within the zone of entrainment. Questions about the impact of entrainment go back a long time. In fact, all the way back to the 1960s when water extraction facilities were first being constructed. This is just a tiny vertical slice of the literature. I really just want to hit two major points here. The first is that entrainment has been suspected as a contributing factor in the decline of several species in the Delta, including longfin and delta smelt, and that there has been a considerable effort to understand the population dynamics involved with entrainment, but there isn't yet necessarily a single consensus on the matter. For example, in their 2022 paper, Kimmerer and Gross used smelt larval survey data in a modeling effort that produced estimated mean annual losses to entrainment of around 0.8 to 1.5% of the population. And from that concluded that entrainment was not a significant driver in those species decline, or in that species decline, sorry. So this was just a very brief overview of the literature. I'm not really pointing you toward any single one of these papers. They're all great. But what I would like you to do is to understand that this is an ongoing conversation, and it's one that the Larval Entrainment Survey aims to contribute to. So with each year of our sampling, we have adapted our approach to answer an evolving set of questions. And I'm sure all of you are looking at that and how much time I have remaining and wondering how I'm going to hit all of these. And the answer is that I'm mostly going to be giving you a very brief overview of what we've been up to over these last 5 or so years, and pointing you towards some products that if you want to know more, that you can go and read about what we've been up to, including a few things that are at this very conference. So let's get into where we've been this whole time. We started sampling back in 2022 using methods and gears derived from the Smelt larval survey and 20mm surveys deployed in West Canal, which is just outside the State Water Project. We detected longfin smelt that year between February and March, but that catch later declined to 0 after we switched to the 20mm gear. What our sampling during this first year confirmed for us was that longfin smelt were being directly entrained during their earliest life stages. We also conducted a diel comparison with sampling over several days where we trawled over multiple shifts during the day, night, and early morning. These results were written up in our recent IEP newsletter article, which was headed up by Kyle Griffiths. If you're interested in knowing more, that article is a great place to look. I joined LES in 2023. And for that season, our main interest was comparing our most effective gear, which was the 500 micron SLS net, with a new net, a 940 micron mesh net that was going to be sort of an intermediary between the original 500 micron net and the 20 millimeter net. So we continued sampling in West Canal. And we conducted a targeted gear comparison study where we went and sampled at stations where we knew longfin smelt was occurring through the SLS data set. And we tried out 3 nets, all mounted on SLS sled frames, so the 500 micron net that we've used previously, a 940 micron net, which was our new experimental net, and then a SLS scaled 1600 micron net. If you're interested in the results of that gear comparison, you can check out my 2024 talk, but briefly, we found that the 1600 micron and 940 micron nets performed very similarly to one another, and that overall our most effective net remained the 500 micron. We went into our 2024 season with a couple of questions in mind. We had been sampling in West Canal, but as you'll recall, there's more to entrainment than just direct entrainment. And so to consider the effects of indirect entrainment, we expanded our sampling out of West Canal to a set of 5 SLS stations in the South Delta along what we considered to be a gradient of entrainment risk. We split our sampling into 2 treatments with intensive sampling at 2 priority stations 1 day a week, and then a broader transect run of all 5 stations with fewer replicates on the other couple of days a week. We also introduced a new gear type this season in the form of the bongo sled. This took quite a bit of development, but was very successful for us overall. It lets us mount a pair of nets side by side to sample a larger volume of water than other methods and do it with the same number of toes. More information about this gear shows up in my 2025 presentation. So if you want to know about what it was like getting this put together and out on the water, you can check that out. As for our season results, well, I explored some factors like seasonal timing last year using a permanova and found out that while those had some effect, it was likely that other factors were shaping our abundance data. And if you're interested in understanding more about what was going on that season, I would actually point you toward a poster that I contributed to, but was primarily headed up by Virginia Afantoulis and Kyle Griffiths, which is right upstairs. They've done some really great work following up on that initial investigation. While you're doing that, I'd like you to also take a look at Lelena Hablutzel's poster on longfin hatch timing in the SLS data set, which while it's not using LES data, it still has some really interesting implications for our study and others working with longfin. Going a little deeper into the 2024 data set, one of the things that we got interested at this point was depletion. One of the things that sets LES apart from similar studies, our sister studies in the Stockton office, is that we're conducting replicate tows at a smaller number of sites, potentially skewing our catch downward if the fish available are being depleted. To investigate that, we set out to see what effect the sequential tow number had on our catch. Because we sample sequential replicates, if depletion was occurring at a significant level, we would expect to see a decline in the overall density across all toes. So what I have displayed here is the mean longfin catch from our 2024 season. And as you can see, there does not seem to be a really clear pattern indicating the catch declines with replicate toes. And that held in further runs of the same analysis when examining the catch of the highly abundant prickly sculpin, as well as with a negative binomial regression that supported this interpretation. So while we're carrying out replicate toes at these stations, these aren't shallow streams or isolated pools. These are quite broad riverine channels with enough fish present that, at least for the methods that we've outlined, depletion does not seem to be a factor, and toes are independent from one another. I'll briefly highlight that we also completed a second diel comparison special study in 2024. The outcome of this study showed that we did not find a significant difference in the number of longfin present during the day versus at night. We did find that there was a degree of seasonal effect in our sampling, which is an interesting contrast with our 2022 results, which were the opposite, which really kind of underlines to me what a different habitat we're sampling compared to West Canal. Getting into 2025, our conversation at this point was turning into questions about detecting our target species and the variation within our catch. So we decided to shift our sampling away from our self-delta stations to a downstream control station, which we knew from previous SLS data was the locus of consistent longfin smelt catch during their spawning season. This new station gives us a control to consider questions around the presence and absence of longfin smelt in our sampling. Over these last few years, our sampling design has maximized the number of toes that we perform during each sampling day with the aim of addressing the question of detectability. Following earlier work conducted on detection probability using the 20 millimeter data done by Maharja et al. 2017, we're then going to use the R package unmarked to perform a single season occupancy model. Calculating detection probability this way accounts for both the probability that smelt are present and also the probability that smelt are present but not being detected. This paired approach will help us identify differences in detection probability among stations, and the 3-year data set for stations 809 and 812 will help identify how annual variation impacts their detectability. All right. Detection probability can help us identify how many toes we need to do to detect longfin smelt when they're present. But as I mentioned at the top of this presentation, our goal is not just to detect longfin, but to quantify them. So we need estimates of how many longfin smelt are present. As I found in my investigation into depletion, variation among toes in our data set is high. The higher that variance, the more toes it takes to maintain a targeted degree of certainty on any estimates of abundance. So the more toes, the tighter your confidence interval. From a modeling perspective, this seems very clear. We just do an infinite number of toes. And that certainly has no consequences whatsoever. But no, in fact, we need to accept some degree of constraints by just plain physical reality and the endurance of our crew. And instead know what effect changing the number of toes has on our data set. So one of our goals with this paired station approach is to account through modeling for the sources of this variation within our abundance data. Ultimately, we would like to provide both an estimate of abundance along with a range of confidence for that estimate, which is pretty cool, right? This is the point where I pivot to my 2025 data and show off all the cool stuff we're doing with it. But at this point, I hope what I've mostly done is piqued your interest. We are still in the process of processing our 2025 data, even as we're out on the water in 2026. So we've continued sampling pairs of stations to inform our modeling effort, but that isn't the only thing that's different about this year's sampling. This is also going to be our longest year of sampling, starting in January and running all the way through June. We're also trying out new things with our gear. As you recall, we use a dual bongo sled design, so it's these two nets mounted side by side. In previous years, we've had two 500 micron nets mounted to that. This year, we're running a single 500 micron net with a scaled down version of the 20 millimeter net, 1600 micron net, which will allow us to compare those gears directly. All of us with the LES are excited to keep informing the conversation around entrainment with products like a final report on our sampling through 2026, including seasonal results and other products synthesizing what we've learned over the last few years. In the middle of all this, I didn't have time to talk about one of our most exciting elements, which is collaborating with DWR's genetic monitoring lab. I swear I'm not just introducing Christina for this next talk, but she'll be telling you a little bit about that. We're very excited to be participating in this work. And I'll conclude here by noting that while I say I quite a few times in this presentation, should really be saying we, except it sounds weird. I am remarkably fortunate to have a lot of people helping me out with this and driving this project forward, whether that's out on the water, collecting samples in the lab, or running this conference. So thank you all, and I'd be happy to take any questions if I have time.
We have time for a couple of questions.
Hi, that looks like good work to me. I would challenge, though, the idea that you could take replicate samples at all in a moving frame, in a moving body of water, because you're sampling at a fixed station, and in between toes, the water has moved on. And we all know how patchy fish can be in the water in their frame of reference. So how do you get around that? How do you explain that as replicate toes?
I think the best thing to do when you're dealing with a situation where variation is high, as I mentioned, the more replicates that you can perform, the tighter that confidence interval, the more that you're going to encounter.
Yeah, that's true, and that's just a consequence of statistics. And the more you can take, the better. I agree with that. But the idea of them being replicates of each other, I think, is flawed. And I think, in the 20 millimeter survey, you see it, the water moves like a kilometer between toes.
I think that's an interesting critique. I need to track you down. Let's chat. Anything else? Sweet, thanks y'all.
All right, our next speaker is Christina Burdi with the California Department of Water Resources.
Hi, everybody. So I'm here to present on the eDNA aspect of the LES survey that Morgan just talked about. And just some basics about eDNA. eDNA is DNA that that an organism leaves in its environment, such as skin, blood, feces. Some of the benefits of eDNA sampling is that its detection is sensitive and non-lethal, which makes it a great method for sampling rare species. It's cost-effective, faster, and less labor-intensive than traditional methods such as trawling. Some of the challenges of eDNA is that the signal and concentration is influenced by turbidity and hydrodynamics, which means that the methods and interpretation can change based on a sampling site or day, especially in a system such as dynamic as ours. So Morgan already got into a little bit of this, but since our eDNA is pairing with the larval entrainment survey, just some basics. The larval smelt take is not quantified at salvage facilities. So the 2020 ITP wanted to try and mitigate this by mandating a new larval entrainment monitoring program, which was the LES survey conducted by CDFW. And we wanted to add eDNA sampling to improve quantification and detection sensitivity to that. So before I get into last year with our co-sampling, I just want to do a quick recap of what we've done so far. So we started in 2023, and we just had the basic question of, do larval delta smelt shed eDNA? And then we also wanted to see how eDNA is affected by abundance. And we did this by conducting a bucket study at FCCL. We put known quantities of larval delta smelt in a bucket of 15 liters of water. And then we filtered out the water using Sterivex filters and tested that for eDNA. And so we found that yes, in fact, larval delta smelt do shed eDNA, and that eDNA increases with abundance. And also something really cool from the study was that we were able to detect one itty bitty larvae in 15 liters of water. And there's a great picture here that shows you just how tiny those little guys are. And so we wanted to take what we learned in the field, in the lab, and bring it into the field. And we conducted field surveys in both 2023 and 2024. 2023 was a very unusual water year, so that's why we continued it in 2024. And we again wanted to see how eDNA is affected by varying abundance and then also distance in the field, and what is the best field sampling method. And we did this in West Canal. And we also did it with what's called a live car. A live car is essentially like this metal mesh cage, in essence, with a mesh bag of live larval delta smelt inside with known quantities. And then we put little pool floaties on top so that it floats on the surface of the water. And then we sample in this serpentine pattern going against the flow from the live car. And we did this using Smith root was one of the field methods. And we use the Smith root because it's generally easy to bring into the field. You even get a cool little backpack for it. The filters are self-contained and also stable at room temperature. So you don't have to bring a whole bunch of ice with you. We also used a tonet. The tonet allows us to sample a larger volume of water and thereby has a higher sensitivity for eDNA. We use Sterivex filters, which is considered the gold standard in eDNA sampling. And then for 2023, we also used the ESP, which is Environmental Sample Processor. It's an autonomous sampler on loan to us from Barney. And this is able to be programmed and take samples for you. So getting into some of those results, what we found was that the tonet is by far the best method. And that's just because we're able to sample a larger volume of water. And then the Sterivex is the next best after that. We found that with increasing distance from the live car, eDNA decreases. And then with increasing abundance or number of fish, eDNA increases. So taking what we learned in 2023 and 2024, we wanted to move into that co-sampling aspect. And in 2025, we paired eDNA monitoring with the CDFW larval entrainment survey. And basically the question for this year was, can we do this? Like, can we pair eDNA with this survey, and also can it be accurate? Typically in eDNA sampling, you're going to be bleaching the nets after each sampling, or each tow even. You're going to be bleaching the boat. You're going to be bleaching everything that you possibly can. And that's just to reduce contamination. You can't do that with the CDFW boat. They need their boats. You can't do it every time. So again, we just wanted to see, can we collect accurate data based on that possible contamination? And so due to the fact that we didn't know if we could even collect accurate data on the CDFW boat, we paired that with a DWR clean boat to see what we could. And we tested for 4 species. We looked at Longfin smelt and delta smelt, prickly sculpin, which is a very common species around this time of year. And then we also used ballyhoo. For those of you that know what ballyhoo is, this may seem a little weird, but this was used as our positive control. Ballyhoo is a species that's in the Atlantic and then also tropical waters around Florida. So it doesn't exist here. And so that's, again, why we used it for our positive control. Okay, so we did this with a big convoy, very complicated. I lost some of my sanity, I'm not gonna lie. 3 boats, three essentially agencies. One was a contractor and 4 different sampling methods. And we conducted the sampling in Lower San Joaquin, so bigger body of water, more complex than what we did before, at stations 809 and 812. We did this from January to April, and we conducted 3 10-minute tows at each station. So we just had CDFW less survey, well, less, I guess. CDFW survey, we just followed their methods. We didn't do anything different. So leading the charge here, going against the flow, was the Cramer boat, and we towed what we called a dynamic dead car, or the Schreier method. And we essentially took the live car and weighed it down so that it's more in like the middle of the water column, and we put dead ballyhoo in there for our positive control. Then next up, we had the DWR clean boat, meaning it was bleached before each sampling period, and it sampled in that serpentine pattern behind the Cramer boat. And we used tonet sampling and also Stereovex sampling based on our results that we got from previous studies. And then, of course, we also took boat swabs and controls just to see if we had any baseline contamination. Okay, and in the back, we got the CDFW trawl vessel conducting their regular larval entrainment tows. And we took water from the cod end to sample for eDNA. And then we compared that water to the fish sample, the physical fish samples that were collected in the trawl. And then we also, we added what was called passive samplers. This is a method that's been used in other areas for this kind of thing, with pairing with other monitoring. It hasn't been used here before. And passive samplers are essentially a wiffle ball with what looks to be a kitchen sponge, but more complex and considerably more expensive. And so the kitchen sponge is inside the wiffle ball. And because it's like self-contained like that, it is added because we wanted to reduce the risk of contamination. And so the passive samplers are just clipped to the net bridle, and so it's towed in front of the net, just like with the regular sampling that they're already doing. So that's how we added on there. And then we also took boat swabs and controls to see for baseline contamination. Okay, I have a lot of results. So I'm gonna try and make this as digestible as possible, and I limited some as well, just for your sanity too. So first up, we're gonna look at the results from the CDFW boat. And we wanted to see, again, what the baseline contamination was. And then we used that with the swabs. And ultimately, there's a lot. It's everywhere. So not really a big surprise. We weren't able to bleach the boat beforehand. So this just gives us that the boat is contaminated with DNA. Again, so looking at the cod end controls, and I'm just gonna show you ballyhoo here. This is just the controls of water flowing through the net between each tow. So there should be no eDNA, and well, there's still a lot. So ballyhoo still is existing between tows. And one of the things that I wanted to point out here was that ballyhoo eDNA is lingering between sampling days. So if you look at the last tow on January 22nd, and then the very first tow on February 5th, before the net was even in the water, very first control before the net was even in the water, the eDNA for ballyhoo is lingering. So it's lingering for 2 weeks, which is crazy in and itself, but it tells us that this is not a feasible method for sampling eDNA. Okay, passive samplers. So huge deal. No contamination with the passive samplers, which is great considering the fact that we have a contaminated boat. And just to show this graph a little bit, so on the x-axis, we have, like, in essence, the time series. It's starting with the very first tow of the day, going to the last tow of the day. For this year, we only did station 809, just because we weren't sure if we wanted to print all these passive samplers. And then on the y-axis is just log relative concentration. So overall, they're successful. We got detections, that's great. And the detections varied compared to the trawl met. So we had some instances where the passive samplers and the trawl net got the same species at the same time. We had some instances where the trawl net got fish species that the passive samplers didn't detect. And then we also had instances where the passive samplers caught species that the trawl nets didn't detect. And so in this instance, it was delta smelt in 2 different instances. And what we looked at was that EDSM did catch delta smelt in the area. Still processing some trawl samples, like Morgan said, they're still processing a lot. One of the things that's interesting to look at here is that in March and April, we didn't get any detections with the passive samplers. We don't know what that means yet until we have the fish samples to look at, so stay tuned. Okay, just real quick, DWR boat results. And essentially all of these results, not only DWR, but also CDFW as well, like hot off the presses. So we just have a little bit, but, and I want to kind of show you that the y-axis is essentially switched in how you're thinking of it. So it's not only log relative concentration of eDNA, it's just the CQ values that we get. And so in this, you kind of have to think that the lower the CQ, the higher the eDNA concentration. And so we got some results. Longfin smelt was detected in all but 1 toe, and that 1 toe happened to be a toe that CDFW didn't catch longfin in their net either. And then it also, the toe net also got some detections that the passive samplers missed as well. And then we're still doing the qPCR for more species and dates. Okay, so to sum it all up, we had the basic question of, can we add accurate eDNA sampling to CDFW monitoring? And yes, we can, but not via the Kurthen, despite the fact that it's incredibly easy. We just can't do it because the net isn't bleached in between. But we can use the passive samplers. Those were successful. There was no contamination despite a dirty boat. Again, it's the first time utilizing this method in the estuary. It's easy to implement, has wide utility. We're actually pretty excited about this. The DWR toe net is highly successful. We got positive detections in that wasn't found in other methods. However, it's not good for pairing with CDFW monitoring. And that's just because you're gonna have to have a separate boat each time that's clean, and it's just not good when they're going out weekly, and that's just not a good thing. So ultimately, we are conducting some of the foundational eDNA work here, and we're understanding our limits. We're determining which methods are best for which situation. And ultimately, not one eDNA method fits all. The toe net is best for separate studies where you have the ability for decontamination protocols. The autonomous sampler is a great method because, again, autonomous, it does the collecting for you, you're able to program it, but we needed more flexibility. We needed something that we could like pick up and take with us. With this particular sampler, it's static, and so we weren't able to, it's not as transportable. Some of the other eDNA studies that are being conducted in our lab are using other autonomous samplers, but we're not looking at it for this project. The passive samplers were great for this. It had a reduced risk of contamination, easy to pair with other studies, and a wide variety of uses. And so for this year, we are leaning into those passive samplers. We're refining our passive sampler methods. We're focusing on the logistics. Less survey is taking them out weekly during their sampling, sometimes twice a week. And so we're just seeing how the logistics work out with that. And we're also doing different temporal scales. So instead of sampling each toe with the passive samplers, there's some that we're leaving out for each station. And so we're trying to see how that varies. And then also different stations as well. Les is doing station 513, like Morgan said, in the confluence. And so we're adding eDNA to that too. Giant project, so many people to thank in the field, in the lab, all the different labs. so much. So thank you, everybody. I'm sure that there are more here that I forgot, and I'm very sorry. And with that, I will take questions if I have time.
We have time for a couple of questions.
Thanks, Christina. That was great. So with the hullabaloo, with the ballyhoo, I'm wondering if you know how long your primer is for that species, and I wonder if there's potential for another species, even one that's not closely related, perhaps having a similar sequence in its DNA.
I am not the genetics expert for that. So if there are maybe Daphne or somebody else that wants to answer that question, either now or later.
Yeah, I don't know. Sarah Perry, do you know the length? Okay. Yeah, I don't know exactly the primer length. I do think some cross amplification would probably be pretty unusual given the species that are in our sphere.
For those of us that aren't as familiar with the eDNA, this is kind of, I wanted to see if you could elaborate on that ballyhoo. So is it typical that eDNA sticks around for so long, like 2 weeks, that you could detect it and that somehow, does that complicate your sampling? And you know what I mean? Like,
I don't think that's typical. I think this is something that I mean, again, I am also not a genetics expert. I'm learning.
It all depends how long the DNA sticks around in the environment. In this case, if it's out of the water and kind of hanging out, it could stick around for longer. But in the water, we typically the signal we lose the signal very fast because of the fast moving water and the enzymes and stuff that are in the water.
Yeah, so it's likely coming from the net, Brian.
This is the control, so this is
Yeah.
information that was staying on the net, not contamination. Not a signal that was in the environment for 2 weeks. So it was just sitting on the net while it was in storage for that 2 weeks.
We have time for one more.
Maybe a question I can actually answer.
We'll see. Awesome presentation. The question I had is for some of these controls, I always wonder, like, how do they relate to real abundances of organisms? So the one larva in 15 liters, like, how does that relate to what we actually see in terms of delta smelt or Longfin smelt concentration, quote unquote, concentrations or volumetric abundances, densities in the environment?
Yeah, so I think what is important in the one larvae in 15 liters of water is that you have just essentially a really small amount of eDNA and you're still able to detect that. So as far as how it relates out into the field, I mean, I guess it could be something like when you have a really rare species and you just happen to have 1 or 2 or 3 in a larger body of water. It's pretty cool that you're able to detect eDNA with such a small amount of fish. Okay, thanks.
Thank you. Excellent talks. Again, we apologize for cutting into your lunchtime a little bit because of our technical difficulties. Please be back at 1:30. As always, we remind you to be safe walking around downtown. There are a couple food trucks, JoJo's Hawaiian at 1651 7th Street, Gondo's truck at 1150 N Street. But again, please be back at 1:30. Thanks. All right, we're going to get started promptly at 1:30. So please take your seats soon. Thank you.
Good afternoon. Hope everyone's awake post-lunch. We are going to start session 10, physical and biological effects of flow. First up, we have Wim Kimmerer presenting on variable freshwater flow, estuarine circulation, and food web interactions, regulate abundance of the endangered longfin smelt. Give him your attention, please.
Thank you. No clapping, I don't have time for it. Okay, so move this. Uh-oh. Can't even work this thing. Use the rodent. Okay, here we go. Oh, I see. Okay, so here's what I'm going to talk about. Longfin smelt, you know, the decline, you know. Key influences. Maybe you know some, maybe you don't know all of them. I don't either. Thank you. All right, we're going to use show you some particle tracking work to infer their vertical movement. Whoops. And cutting out here. And then recent findings about spatial distribution. So, and remaining work on our project. So just a little introduction. We've got a rather large interdisciplinary project, well-funded on longfin smelt. 2 years of field work that we've done, but we have a lot of catching up to do on what that implies. Some background, you've all seen this before. I can barely see this stuff, so. No, I can see that, but I'm trying to see the notes view. Anyway, it's okay.
You sure?
It's okay. Yeah. Yeah. Anyway, so you've all seen this canonical, decline picture, and there's a few things I want to point out about it, and let's see if I can. Yeah. Nope. I don't know how to make that go. Anyway. So one thing is, you see a downward trend, and you see a lot of variation. And you also see a line. You didn't tell me you didn't see it. I should have practiced, I guess. Yeah. So you see a line, and maybe you can see my. No? Okay. And there's an error band around the line, and that line is from a linear model with two things to it, x2 and time, so year. So it's just saying, okay, they're going down and they're varying with flow. And they vary by about 100-fold with flow, which is quite a lot. So that's the range of variations, 100-fold. And that's the short-term variation, all that short-term fluctuation captured by the line. And then the little dots are the data. But then we have this, this decline that started in 1987. And that is almost certainly due to Potamic orbula and its effect on both phytoplankton and the zooplankton. I'll show you later. And on top of that, we've got some mystery data points the last 5 years. when the model utterly fails to predict what was the actual abundance. And so what's going on there? Well, has the decline stopped? We're not quite ready to say yet. We can't say because we've had high flow years, several in a row. And so it remains to be seen, but if that decline has stopped, it means that there's a new carrying capacity, and that's where the population is. So what limits the population size? Well, I mentioned Potamicorbula, and it's due to, the effect is due mainly to Potamicorbula's direct effect on copepods and direct effect on phytoplankton, which is indirect to copepods. And I'll show you that in a little bit. You've probably seen it before. But then we also have the effect of anchovies, which we're kind of viewing as sort of an additional causative factor limiting the seaward extent of the population until the fish get big enough to be competent. So here's the annual chlorophyll patterns. The upper panel is from pre-Potamicorbula, lower panel is post. The light blue is the wettest years. And you can see that there's, that's the median summer biomass. And after the clam, the median summer biomass is down by a factor of about 5. Well, that's a big drop, and it caused a huge effect on the copepods, which underwent a similar kind of decline, except it's much shorter. So everything we see, so Eurytemra caroleae, not a finis, every year comes up in the spring and then drops sharply right about the time that the longfin smelt need to eat them to finish growing big enough to be able to switch over to mysids. So why Eurytemra? Well, several studies, and I forgot to put on here the one by Lojkovic, Burris, and colleagues. They all show that Eurytemra caroleae is like 2/3, 3/4 of the diet of longfin smelt larvae. And when they get to about 25 millimeters, Arthur Barros showed that they start switching over to mysids. And that's an important thing to remember, because that's an important thing in the life cycle is when they switch to larger food, and they have to become competent to do that. So I'm going to talk about particles. Why particles? Well, these animals live in a moving frame of reference. The water moves with tides, it moves with net flow, and because it moves, fish move with it unless they can do something else. And I'm going to show you that, yes, they can do something else. So I've been working with Ed Gross for years and years. Ed is a really good particle tracking modeler. When I say particle tracking, I mean these are virtual particles in a computer. They're just sort of imaginary points that move with the water. And so wherever the water goes, they go. Where there's turbulence, the net flow at the surface, net flow at the bottom, whatever. So what you can do with a particle tracking model is you can give the particle behavior. That's what he does. And what this shows is this is the sort of setup for a particle tracking run where the different parts of the estuary are sort of balkanized. And this was part of his study on the hatching regions, inferring hatching from where the fish are and hatching locations using a particle tracking model and then back calculating where they came from. So these are our particles here. You can't quite see them when they're in the delta. They were all released in this red zone, and here are some of them already coming out in the ocean. I think that's 2 weeks later. So just to give you a little orientation, an X2 value of 81 kilometers means the low salinity zone about where the red line is, and at 57 kilometers, it's about where the blue line is. And those two places are extremely different. The main thing is bathymetry. So that's something I'll say a little bit about later. But when he releases those particles, the ones that have sinking behavior will stay put in certain places. So here's some particle tracking results. This is from that release site, that red release site, near the confluence. Particles that under low flow, particles that are passive, that just go with the water,
will leave the estuary completely within about a month. And that's spread out over time, of course. If they do that under high flow, they're gone in a week. So if you have really high flow, and if the fish weren't doing something to stay put, they would be gone in a week. A very, very brief period. Now, what about particles that sink? The sinking particles, whether it's low flow or high flow, they stay in a very narrow salinity band between around 0 to 5 salinity. And that's a key range. So in the estuary, we have a bunch of deep spots. And the deepest one is at the Golden Gate, but that's not important for longfin smelt as far as we know. But the one in Carquinez Strait is extremely important. And I'll show you some stuff from there. So our project included field sampling in 24 and 25, day and night, and mostly using a 20 millimeter style net, the same net that Colin's program does. And so so here's where we sampled in 24. So we sampled by salinity. We sampled deliberately across the salinity gradient because that's the habitat of the fish, right? So we didn't look at the map to know where to go. We looked at the salinity. We had to find a high salinity, medium, a couple of medium salinities, a low salinity. And so we were spending some time hunting around. And these symbols are the spots where we sampled over the season. So we started in March, we went in June, and the salinity gradient gradually retreated to the east toward the delta. But we never sampled in the delta. And the reason is that the salinity gradient never got there. So we were sampling across the salinity gradient to see where in the salinity gradient the fish occurred. Now we knew from the 20 millimeter survey that they're pretty much in 0 to 5 salinity, but we didn't know what they were doing at the bottom. And so now we know a bit more about that. So we sampled along the gradient. Now this is I have to explain this diagram. 2 panels. The upper panel is daytime sampling and the lower panel is nighttime sampling. The white line is the bottom and it's heavily distorted because of needing to make the vertical visible. And the little blobs are samples, and the empty little blobs are samples where we caught no fish, and the filled blobs are ones where we caught fish, and the catch is represented by the size of the blob and the brighter yellow color. And what you see is that most of the catch is up here. Well, this doesn't show you the salinity field because it's kind of hard to show both because we're sampling over time, right? So what this shows is basically, when the fish were up in this region, they were mostly caught, well, they were caught over a very narrow physical, spatial distance, but an even narrower distance in salinity space. I think we caught about 2/3 of the fish that we caught between salinity of 0 and 5. Maybe it might have been a bit more than that. So, in total we caught almost 3,000 fish in 2026, which I'm not going to show, or 25, I mean, which I'm not going to show you. We caught about 8,000. There were a lot more of them out there. And so why are the fish in that low salinity? Well, when Ed puts his particles in his particle tracking model, and they have sinking behavior, which you can just tell them, when you're in the water, just sink at such and such a speed. It's not too fast that they go to the bottom. Then they will be in this same salinity range. And we've known this for years, right? How many of you guys know where the Benicia bump is? We've seen the Benicia bump, yeah? Okay, so the Benicia bump is kind of a shoal near the Benicia Bridge. And it's there because that's the furthest seaward this intense circulation can exist. Because what happens is the salty water coming in at the bottom hits the shoal there, and it goes up and slows down, and the sediment settles out and forms a bump. So I didn't say this, but in Carquinez Strait, it's always stratified in salinity. And in high flow years, it's intensely stratified, like 5 at the surface and 20 at the bottom. And everything changes. So we were seeing sand waves on the bottom up to 5 meters high, and which sounds ridiculous, but there's such a strong flood flow with the tidal energy and the salinity gradient forcing this water to dive under the other water and zoom east along the bottom. Pretty exciting place to be on a nice night trip. So, oh yes, I forgot to put that on. Anyway, got through that. So this is our catch results from 2024, and it shows the size distribution over time. And the yellow is daytime, and the blue is nighttime. And oh, I forgot. I'm going to go back one and say the distributions at night weren't all that different from daytime, which amazed me. I thought they'd be totally different. So we learned something on that. We learned a lot. Anyway, back to the size distributions. This is almost exactly the same as we see in the combination of the Smelt larva survey and the 20 millimeter survey. You see them, they kind of don't seem to grow when they're in the early part of the year. So we're using both of those nets, the Smelt larva survey only in 24 because we didn't like it. The Smelt larva net, I mean. And then you see in the 20 millimeter net, they're apparently growing, and then they're apparently leveling off. Well, what's going on there? They're not, and they kind of disappear. They start to dwindle. This is our last sampling day. But in the 20 millimeter survey, which goes longer, they pretty much disappear. So what's going on with that? Well, they're graduating. So this is what you see with bigger nets. So this is a summer tow net survey, and the net's 4 millimeter mesh instead of 1.6 in the 20 millimeter survey net. And then this one is the base study, which has I think it's a 10 or 12 millimeter net. No, centimeter. And no, that can't be right. Anyway, it's bigger. Anyway, one thing about that net is that it doesn't catch small fish very efficiently. And so the long base study people cut off the data at 40 millimeters, saying those data are no good, which is unfortunate. But anyway, what it shows is that there are bigger fish out there. And that's not all. Now this crazy graph, I have to apologize for an AI error on it. This is each panel is the length distribution of fish in various places. And basically what it shows is, I'm gonna have to zip through this, is that in April and May, in the smaller mesh net, our net, all the fish were small, almost all the fish were small. And then when you look at the larger nets, larger surveys, a lot of them are much bigger, and few of them are small. So what next? We have samples to analyze. We have gut fullness to figure out. We have distributions in lots of directions and dimensions that need to be figured out. An otolith analysis from Levi's group, which I can't wait to see because I want to see how that relates, how growth rate relates to feeding rate, and how salinity history relates to where we were catching the fish. and movement patterns and retention, and predation effects of anchovies, which you've heard about before. So these are kind of the key people. I'm just gonna kind of skip over this. Thank you. This is the crew. Ann Slaughter and Tony Guffel right there. We're our stalwarts on the boat. Jason Hastrick is our project manager. Ed Gross over here, a modeler. Michelle Youngbluth doing the diet studies in her lab. And then Levi Lewis, sorry Levi, I had to put you on a different level here. You're on a different plane. Lenny and Sean, who really kind of helped us get this funded, get it going. And then lots of agencies and people and funding sources to thank, especially water contractors and the Department of Water Resources. And I want to thank Bryan and Darcy for that. And I want to thank these guys.
We sadly do not have time for questions. Next up, we have Angelika Kurthen. How complex is too complex? Probing flow abundance relationships in the San Francisco Bay Delta.
Good. Thank you so much. Hi, everyone. I'm Angelika. I am new to the system. So I just finished up my PhD this summer at Oregon State University doing community modeling in the Grand Canyon region. And now I'm kind of applying some of those methods of community analysis to the San Francisco Bay Delta. And I'm looking at different models of flow abundance relationships within this system. And I'm working with Albert Ruhi at UC Berkeley and in collaboration with Sam Bashevkin and Laura Tortelsheb at Waterboards. And just an outline, so I'm going to explain the project goals and the research question that I'm working on. I'm then going to kind of talk about time series community data as an opportunity for looking at biotic and abiotic variables. I'm going to present some one-fish models with and without food web interactions and kind of compare those. And then I'm going to talk about some next steps and where I hope to go with this project. So starting out, the primary research question that I have is that of basically complexity. Does considering or not considering food web interactions in models affect our understanding of flow ecology relationships? And this question of incorporating biotic interactions in models is a kind of like a fundamental tension in community ecological theory and in its practice, right? So studying food webs themselves are hard. Interaction strengths are usually found through kind of experimental analysis, often without flow, like experimentation occurring concurrently. At the same time, flow ecology relationships are usually estimated based on flow and population abundance. So putting, typically flow on the X, abundance on the Y, and modeling that. Those are two fundamentally different methods. And so that leaves the question of when we look at time series of a population of a community, how do we know if the trajectory is driven by the environment, so the abiotic factors, or by competitors, predator-prey relationships, consumer resource relationships, so the biotic factors? Is it neither? Is it both working on this at the same time? And we can do this with long-term data sets. And so one great thing about the San Francisco Bay Delta is we have excellent long-term data sets that have both biotic and abiotic factors. And what we can do is use time series analysis to investigate these questions. And so we're using a method called multivariate autoregressive models, or MAR models for short. These models allow us to partition biotic interactions from abiotic interactions, and we can also kind of partition that from process error, which is a fancy way of saying unexplained variation that doesn't include biotic or abiotic interactions. And this method has been used in the estuary before. So I think the most famous example is McNally et al. 2010. That was, I think, the first example of this being used, and it's been used in a handful of other studies. Here are like just a few. There's more. This is just a subsample. And so the overarching goal is to create a large model that looks at flow ecology relationships for multiple fish taxa, the 9 included here, zooplankton taxa, benthic invertebrates, and chlorophyll. So look at the whole community. However, we have to start out small. So we're focusing on one fish species and kind of simple groups in one region, and that's San Pablo Bay. So we're looking at longfin smelt. We're kind of grouping together our zooplankton, our benthic invertebrates, and our chlorophyll as a proxy for phytoplankton. We're looking only in San Pablo Bay. And the reason for this is because these models take a really long time to run. They take like 18 to 20 hours to run. So we want to debug the workflow, and then we can scale up so that I'm not spent like hunting down commas in the code. So basically, this is the fundamental math of the model. And what we want to get out are the biotic interactions highlighted in red and the flow coefficients highlighted in blue. We also get process error, but we're going to not talk about that. And this is going to help us understand how does flow ecology, so those flow coefficients, respond to the inclusion or exclusion of food web interactions, those red biotic interactions. And we have a bunch of data that we can then put into the model. So we have Bay study and EMP seasonal average abundances from 1995 to 2022 in San Pablo Bay specifically that we're gonna put in. We're also gonna feed in kind of matching flow data, so average January through June delta outflow from 1995 to 2022 from day flow models. And to kind of dive into the biodata, we're looking mainly at age 0 longfin smelt. So we have a length cutoff that we're looking at, and we're including all data in the Bay study for that. For our zooplankton, we're combining like 6 different taxa. For our amphipods, we're combining 2 genera. For introduced clams, Tamacorbula is the main one. So we're only looking at that, and we're using chlorophyll A as a proxy for phytoplankton. And so what's wonderful about the base study and day flow is that we have data at a really good resolution. So we have monthly data. However, we want annual time steps to match that annual fish dynamic related to recruitment. And that means that we have to look at the kind of year in the life over 1995 to 2022 to make sure that we're choosing the correct seasonal windows to look at and average over. And so in this case, we have % total catch per month over the course of the average year for each of the taxa. The darker the color, the higher the % of the total catch. And as a reminder, we're looking at January through June flows. That's kind of when that big flow pulse occurs. And so we want to make sure that we're matching that. So for the longfin smelt, we're trying to make sure that we capture that pulse that we see kind of in June, July in San Pablo Bay. So we're choosing an April through October seasonal window. And for our zooplankton, our amphipods, our clams, and our chlorophyll, we're averaging over March through September, trying to capture the peaks in that as well. And the reason why we're trying to kind of get these all around in the same seasonal window is so that we can look at direct biotic interactions and make sure they're co-occurring when we're actually looking at them and averaging them. So this is the mini food web that we're working with. We have longfin smelt, zooplankton, amphipods, introduced clams, and chlorophyll. Not all of them technically interact, and so we excluded those interactions because MAR can only handle direct interaction. So predator-prey, kind of in the same trophic level, competitive or consumer resource interactions. And so as a reminder, right, we ran these models with biotic interactions and without biotic interactions, and then we report the flow coefficients for both models. And so this is what the flow coefficients without biotic interactions look like. So this is in blue. On the x-axis, we have the actual coefficient 0 is that dashed line down the middle. For each of those bars, the dot is the mean estimate for that taxa. And the actual the bar is the 95% confidence interval. And so if that bar crosses the 0 line, it means that there was a non-significant, or basically a 0 coefficient. When we look and compare that with to the coefficients of biotic interactions, we see that there's no significant difference. So this means that the flow effects are the same coming out of this model, whether we include biotic interactions or not in this mini food web. And so then that bears the question, which model is warranted? And so we have a pretty statistical way that we can do that. We have an objective method that we call the IEP's information criterion, or AIC. And in this case, this basically looks at goodness of fit of the model data to the observation data, as well as number of parameters estimated. And basically, the lower the number, the better. As you can see, the model with no biotic interactions technically has the lower AICC and is, technically speaking, the better fit model. That doesn't mean that food web interactions aren't important. It just means that the inclusion of those biotic interactions adds kind of extra complexity that's not necessary to better the understanding of these flow coefficients. And so then now I can tell you some stuff that you probably already know. We can dive into the actual results. Longfin, smelt, and clams are positively affected by flows. We just listened to basically like 2 hours of people talking about why longfin, smelt are positively affected by flows. This has been found before. This is just an example using MAR from Colombano et al. 2021, pretty much the same result. This is probably because of enhanced recruitment, survivorship, shifting X2, more prey availability. The clams are a different thing. The Tamacorbula, so the introduced clam in San Pablo Bay, is a saltwater specialist. And I found this from Hartman et al. 2024. On the x-axis, we have the previous year's Sacramento Valley Index going from drier to wetter. And on the y-axis, we have the center of the clam distribution from Golden Gate Bridge. At the top, it's farther away. At the bottom, it's closer to the Golden Gate Bridge, so kind of moving westwards. In 2 different sampling periods, and for both, there's a negative slope. So as the previous year gets wetter, the center of distribution of those clams moves westward. And what that might look like is something like this. These clams are following probably that X2 gradient into San Pablo Bay. And that's why we might be seeing an increase. So that's what I think could be happening, but I don't know. So this might be related to that shifting X2. We could standardize by salinity zone, maybe, and see if that would change anything. Amphipods are negatively affected by flows. It seems like this is something that is quite common. I found this from Nichols and Thompson, 1985. This is one of the genera of amphipods that I was looking at. On the top, we have freshwater inflow. On the bottom, we just have abundance. And they noted that when flows are low, there's a lot of amphipods, and when flows are high, so like after a flow pulse, like kind of on the right side of the screen, there is usually a drop. And that's because amphipods are they're benthic, they're in the sediment. Flows are probably a pretty big disturbance and probably just kind of wash them away. There's no effective flow on zooplankton and chlorophyll. And I was digging around in the literature a little bit. Smets et al. 2023 was looking at the effect of flow on phytoplankton and zooplankton in 3 different locations in the delta. And so on the top part, we have the effect of discharge on 3 different types of chlorophyll, and they all see no effect. So that matches what we found. That's possible, that there's just not really a huge effect. For zooplankton, it seems to be dependent on the category of zooplankton. So cladoceran saw an effect, copepods did not. We lumped all our zooplankton together. So kind of moving forward, I think spreading the zooplankton out into categories would be really helpful into untangling those flow ecology relationships within the overall zooplankton group. And so some primary conclusions and limitations. The modeling approach was able to partition biotic from abiotic effects. And the flow responses themselves were pretty robust to understanding the food web. So if you have incomplete food web data, at least in this mini trophic level, you wouldn't need to include that in order to understand the flow effects. Granted, this is just a truncated and like small version of the food web. By no means is it the whole community. And we also did a lot of binning and grouping of zooplankton together. The understanding about complexity needed for these models is useful in the context that these models need to remain somewhat simple in order to actually run. So each taxa or each site even exponentially increases the number of parameters that need to be estimated, which in turn exponentially increases the amount of computational power and time it takes to run these models. And yet at the same time, I still kind of want to split the zooplankton into categories, which is just going to increase that. And we're also still at the beginning of this project. So right now we were assuming kind of a region-specific model, but we're not like bound to that. That's basically a management boundary, not necessarily like we could look at a whole estuary-wide model that allows for dispersal across regions and salinity gradients. We could divide by salinity zones instead of looking only at management regions. We have a lot of options. And so moving forward, the next step is to scale up to include multiple fish taxa and include the biotic interactions between fish taxa in the system. And then way down the line, the goal is to compare these MAR models, which include and exclude biotic interactions, but have a singular flow coefficient for the entire sample period with dynamic linear models, which allow you to capture the change in the flow coefficient over time. So this lets you see if the effects are staying the same over the entire time sampled, if maybe flow benefits are increasing, if they're decreasing. What does that look like over a time period instead of just calculating one flow coefficient for Longfin Smelt like we did in this example? We would have one flow coefficient for 1995, one flow coefficient for 1996, so on and so forth. So that is the long-term goal. I want to thank my colleagues and friends at Freshwater Labs at UC Berkeley. I want to thank Jim Hobbs and Wim Kimmerer for answering my emails about zooplankton and like prey taxa and what fish eat in the system. Thank you to the Bay Study and EMP field staff for collecting the data that I used. Thank you to the Dayflow staff for producing the model output that I used in these models as well. I used PhyloPic for the silhouettes of the different taxa. And I think I have time for questions. Here's the mic. Oh.
Has any effect on the actual flow relationship, since the flow pulses can happen over shorter time periods?
They can. However, so looking at the average flows versus those flow pulses, they tend to be highly correlated across a year. So I think a lot of people also use like Sacramento Valley Index or like that year type of wet versus dry. Those flows tend to be like, if it's wet or it's a high flow in January, it's likely to be like higher flow in February, likely to be a higher flow in March. So we were looking at those, they seem to be pretty highly correlated within the year. Does that answer the question or no?
Yeah, thank you.
Thank you. Yeah, good that you're making progress on this. A couple of things, though, I've talked with Albert, so maybe you too, I can't remember, about the idea that when the salinity field moves, a lot of things move with it and with different time scales. So like, the zooplankton and the little fish will move immediately. The clams will settle in a certain salinity range and stay there. So so when spring flow is high and then it drops off quickly, the clams are in higher salinity, after that initial drop off than they would be otherwise. And usually they're in the low salinity zone after they settle. So it really depends on the flow history and the salinity history. The other thing is that the flow across the bottom of the water is mainly tidal. The net flow is a tiny part of that. So that's what's driving most of the interactions between the water column and the bottom.
Considering that, how would you suggest then incorporating that change in salinity or change what you were just talking about in kind of like a time before? So at time t versus time t minus 1 or time t plus 1.
I think so. It's tricky though, because all these different organisms have different time scales, different rates of development and whatnot. So it'd be hard, but yeah, you'd have to do something like that.
Okay. Thank you so much.
Next up, we have Rosemary Hartman, A Place to Call Home. Again.
Hi, everyone. Thanks for coming to my talk. My title is a nod to a paper by Summer et al. 2013, which synthesized what we knew then about the summer habitat availability for Delta smelt. And what I'm going to present today is the culmination of the past 2-ish years, reassessing for maybe the 50th time, but with more data, the relationship between X2, salinity, and habitat for Delta smelt in the summer and fall. This was a huge interagency effort. I don't have time to list all of my co-authors and helpers and reviewers, but it was a huge effort and huge thank you to all of them. So when I say summer habitat for Delta smelt, we have what is known as the Summer-Fall Habitat Action, which was first developed for the 2008 Biological Opinions for the State Water Project and Central Valley Project to help smelt get through what was seen as the sticking point in their life cycle, the point where you tend to get a bottleneck and things would do really well in the spring, and then summer and fall would come around and the population would just tank. And then they'd do okay in the winter if they made it through. So how do we get them through the fall? Well, one of the actions was what's known as Fall X2. And in the original Biological Opinions, they said that Fall X2 needed to be maintained at 74 kilometers for the months of September and October. In 2019, a salinity control gate action was added. So Fall X2 is about outflow, getting the low salinity zone into Sassoon Bay. The salinity control gate action is about lowering salinity in Sassoon Marsh. Smelt like to rear in salinities of 6 parts per thousand or less. So we need these kind of actions to make this habitat available to Delta smelt. And since 2008, we've had several summer-fall habitat actions. First was in 2011, where we had a really wet year and Fall X2 was at 74 for September and October. This is a graph of the Fall Midwater Trawl Index, which I know you all love. And in 2011, that really tall bar, that was obviously a really good year for Delta Smelt. So we had our first X2 action, had a wet year, Smelt did great. Okay, we're on a roll. But then we had a drought. Sigh. We finally could do another fall X2 action in 2017. But we didn't really see a huge increase in Smelt after that. So started scratching our heads a little bit. In 2018, which was a below normal water year, we had the first opportunity to try out a salinity control gate action. Let's see, we might not have enough water to get X2 really low in a below normal year, but we can operate the salinity control gates, lower salinity in Sassoon Marsh. We caught some Smelt in Sassoon Marsh during the action, increased habitat, seemed to be a pretty good thing. And then in 2019, another wet year, another fall X2 action, and new regulations, new biological opinions, ITP, and we included the salinity control gate as another action during that time. And we adjusted the X2 standard from 74 to 80 kilometers. But then we had another drought. Sigh. 2023, we got to try out our new revamped summer fall habitat action with X2 at 80 in September and October and a salinity control gate operational action. In 2024, we had a salinity, we had X2 at 80 in September, but not October. Get to why in a second. And then the salinity control gates in July through September of that year. 2025, no fall X2 at all, but we did operate the salinity control gates. I don't have all of the 2025 data included, but we do have a little bit. However, in 2024, an excellent paper by Polansky et al. Came out, and it showed that we have a really strong relationship between summer outflow and Delta Smelt population growth and survival. Fall outflow, not so much. Summer outflow and fall outflow are often strongly correlated, but the pattern was really clear that it was a story about summer outflow, which had everyone kind of scratching their heads. Like, we've got this fall X2 standard, but it sounds like summer flow actions are going to be a lot more useful for Delta Smelt. And why are we doing fall X2 anyway? We had several hypotheses about fall X2, from back in 2008. And now we have a lot of data that we wanted to test. Are our hypotheses actually backed up by the data we've collected over the past 15 years? So we started this effort. Those hypotheses included one about smelt habitat, the idea that increasing outflow and moving fall X2 will take that low salinity zone and have it overlap with areas of high turbidity, cool temperatures, and extended wetland habitat. We also said that increasing outflow is going to transport smelt's favorite food, Pseudodiaptomus forbici, everyone's favorite calanoid copepod, into this low salinity zone where they tend to be food limited. Increasing food and habitat suitability will increase individual smelt growth, and this will lead to increased population level survival. The final hypothesis that was really on everyone's mind is that we thought flow actions in summer are going to be better than flow actions in fall. We took a weight of evidence approach. Obviously, smelt are pretty rare. We had to use a lot of different types of data to try and support these hypotheses. But we did have several lines of evidence for each of our hypotheses that I'm going to be walking through for you. I'm just going to show some of them in the report that should be coming out in the next month or so. We have a lot more, but I only have 15 minutes. There's only so much I could get in here. But overall, these different lines of evidence will go towards supporting which season is really the most critical and when flow will be most helpful for Delta Smelt. Starting with smelt habitat, we looked at two basic metrics. One, the number of days where water quality is suitable for Delta Smelt, which was a salinity of less than 6 parts per thousand, turbidity of greater than 12, and temperature less than 22 degrees C. We also looked at the area of the low salinity zone using three-dimensional models. And we took a geographic region approach, not a salinity approach, sorry, Nguyen. Sacramento River in yellow, Sassoon Marsh in kind of that orange color, Grizzly Bay in teal, and Sassoon Bay in purple. I'm going to be walking through most of my results in terms of those regions. Looking at number of days of suitable habitat, here we have the days where habitat is within all those three parameters on the y-axis, year on the x-axis, summer on the top, and fall on the bottom. You can see that in Sassoon Bay, years with X2 actions, especially in fall, have way more days of suitable habitat than the other years. In Sassoon Marsh, it was similar. X2 really increased the amount of habitat, but you also got a boost in years when we did the salinity control gate actions. In the river, we didn't really see a trend with water year type or actions at all. And overall, there were more days where habitat was suitable. Looking at the area of smelt habitat, wet years had more habitat than dry years. This is the number of days, this is the area of habitat in Sassoon Bay by day of year for all of the most recent water years. That dark blue line, I want to point out, is 2011. That was the year things were really good for Delta smelt, and we had a lot of habitat area. So there seems to be something there. Habitat does decline through the course of the year, but the wetter years are always on top, so flow is always increasing habitat. So overall, the SONs showed that in both summer and fall, high flows was increasing the amount of habitat. Same with the three-dimensional modeling. So both summer and fall, flow improved habitat. Looking at smelt food, we looked at the abundance of Pseudodiaptomus forbici from 2011 to 2024 and modeled that versus X2. And we looked at Pseudodiaptomus specifically because in this little plot of just low salinity zone zooplankton by month of the year, the purple and pink are Pseudodiaptomus, adults and juveniles. So they are often over 50% of the biomass of food available for Delta smelt in these regions. We also took that data and put it into a Delta smelt bioenergetic model. This is one developed originally by Kenny Rose and later adapted by Will Smith et al. That allows us to say, okay, how much would a smelt grow if it had this much zooplankton or that much or even more? So for the Pseudodiaptomus abundance, this is just the effects plot from the model and in Sassoon Bay, Sassoon Marsh, Grizzly Bay, and the river. CPUE versus X2. The yellow line is in summer and the blue line is in fall. And there's a much stronger relationship in summer than fall. In the downstream regions, you don't really see much relationship at all in fall. But what does that mean for Delta smelt? How much do they care about that boost in Pseudodiaptomus with flow? Well, the top plot here is the average biomass of Pseudodiaptomus by year, and it can really vary from down around 0.1 milligrams per cubic meter all the way up to 1.6. The average is coming in around at 0.6, and if smelt have that much for the whole summer, they'll grow to about 2.4 grams. If they have 50% more, they'll grow an extra 0.1 grams, 50% less, you know. So this can definitely have a 5 to 10% increase in growth when you get that increase in zooplankton. And more is always better. You know, we have not reached the asymptote at which more zooplankton won't mean more growth. So Pseudodiaptomus, you definitely get way more with high flows in summer than in fall. And the bioenergetic model showed that more will help in summer or fall. When we look at smelt growth, we had several different lines of evidence. We looked at data from smelt enclosure studies. We looked at liver condition, growth as predicted by that bioenergetics model, and growth as measured in otolith data. The enclosure experiments, we had 3 years, 2019, 2023, and 2024, where we had enclosures at Belden's Landing and Rio Vista. Our hypothesis was that things would be better in Belden's Landing because the whole idea is we're making better habitat available with our flow actions. Sassoon Marsh is better than the river, but Smelt did better in the river than the marsh. They didn't grow very well. A lot of them died in the marsh. Fewer died in the river. We were confused. We suspect that the results had a lot more to do with cage effects. You know, it's a very artificial environment covered in biofouling, and they can't actually use the dendritic tidal wetland area in Sassoon Marsh. They can't find their preferred temperature or flow rates. So we're not reading too much into this, but it is one of the, other side of the coin, a weight against our hypotheses. Looking at our bioenergetics, we applied the Delta Smelt bioenergetic model to conditions in each region, observed levels of temperature, turbidity, zooplankton, to see how much we would expect a smelt to grow if it was living in these conditions in each year. And there was a big difference between years, not super surprising, but one thing that I was actually surprised at how well this came out. This top blue line is 2011. So just based on what environmental conditions were like, you would expect it to be a really good year for smelt, and it was. Hey, we did a follow-up sensitivity analysis, and we found that zooplankton was one of the biggest drivers in differences in growth rates between years, but temperature also could play a role. We regressed that total predicted growth against X2 in both summer and fall. We found a really steep correlation in summer, not much in fall. So it was really showing that the lower X2 in summer was giving you more bang for your buck than in fall. But that's just predicted growth rates. We also had a great data set of measured growth rates, thanks to Levi Lewis for sharing his data, based on smelt otoliths collected from 2011 through 2019. We again found a relationship in summer, not in fall. We had another amazing data set from the Hammock Lab and collaborators on liver weight of fish collected between 2011 and 2019. The liver is frequently used as a metric of overall health because it stores energy reserves. And Trinh Nguyen from CDFW led up this analysis. He found that there was a three-way interaction between the size of the fish, X2, and temperature to predict the size of the liver, and found that you get the biggest effect of X2 when temperatures are warm and the fish is large. So usually those warmer temperatures are during the summer rather than the fall. So we found that the bioenergetics, liver, and otoliths all supported a stronger effect of flow in summer than in fall. And the cages were confusing and didn't support any of our hypotheses. Finally, smelt population. Here we're really looking at existing published results from the Delta Smelt life cycle model from Polansky et al. And the individual base model that was originally designed by Kenny Rose and has been adapted by Will Smith that was analyzed with the CSAMP structure decision-making analysis. So that life cycle model has a relationship between summer flow and smelt survival. We just applied the summer flow values that were observed for the past 15 years to that model to get an estimated summer survival by year. And you can see that you got over 50%, sometimes over 80% survival in all of the wet years for the past 15 years, and much lower survival estimated for any of the drier years. And that CSAMP structured decision-making using the IBMR found very similar results, that summer gave you a lot more effectiveness of X2 actions than fall. So that supports summer over fall. Overall, looking at the weight of evidence with this and quite a few other analyses that I don't have time to talk through today, we see that summer is mostly the season where we get the greatest benefits from increased flow for delta smelt. Overall, sorry, this slide is too much text and boring, but outflow creates good abiotic habitat, both in summer and in fall. Yay. You get zooplankton transported downstream in both summer and fall, but there's more in summer. High flows in summer increase the individual delta smelt growth and population survival, but the really good years for delta smelts need to not only have that high outflow in summer, but also be cool and have a lot of food. And years like that are probably going to be less frequent in the future. Again, in the report that should be coming out in the next month or two, we have lots more stuff I didn't have time to show you here. And I will take any questions.
Catch Rosie on the break to ask her some pressing questions if you have any. Lastly, we have Kelly Hannan talking about endurance swimming to close out the session.
Thanks everybody for sticking around. You'll get a break after this. So I'm at UC Davis. I'm part of the Fungi Lab. And today I'm going to be talking about endurance swimming tests and how we can use that to inform risk. And I'm going to use our native California fishes as a case study. So you guys in this room are all very familiar with this, but I'm going to quickly whiz through it. So water in California is a highly contested resource. It supports agriculture, municipalities, navigation ecosystems. And I think this news article does a good job of showing that dynamic where we have the Delta surrounded by one of the most productive agricultural regions in the world. At the same time, that water is also habitat, migration corridor, spawning ground, and a refuge. So the question isn't whether we use the water, we have to. The question becomes, how much risk is there to fish and how do we mitigate this? So in the Sacramento River, it's a heavily altered and managed system. It supplies water statewide, supports over 2 million acres of agriculture. It requires annual dredging to keep ports accessible. At the same time, there's 13 species, or at least 13 species of fish that are considered special status. So it's not a simple system to manage. And so we, again, are trying to reduce risk to fish. And as Morgan also already introduced, one of the major risks to fish in this system is entrainment. So I have a little bit of a different definition of entrainment. I think entrainment happens when fish are pulled into flows that they can't swim out of. This can result in an undesirable habitat or injury or mortality. So this happens, whether or not this happens depends on a couple things. So how fast the flow is, how long the fish are exposed to it, a fish's swimming ability, as well as their behaviors. And so in the Sacramento River, we have over 4,000 water diversions, most of which are unscreened or unmodified for any sort of fish protection. And this leaves them wide open to entrain fish, and weaker swimmers or smaller fish are very vulnerable to these impacts. We also have multiple large-scale pumping facilities as well as annual dredging, both of which create high velocity flows. And swimming ability really matters when they're faced with all of these different intakes. So we need to try to find the point where a fish's swimming ability exceeds the intake flows in order to reduce entrainment. So we can do that by looking at endurance swimming tests. So by all these intake flows, we assume that fish are exposed to a fixed velocity for some period of time. And then we can look at how long a fish can hold position at specific speeds, and that's exactly what an endurance test measures. So we look at time to fatigue at fixed velocities. And again, I'm gonna look at this for multiple California native fishes. So to start out with, we're gonna look at Delta smelt. We've heard a lot about Delta smelt already, so I'll quickly go through this. They're listed since 2009, considered functionally extinct, and we are dumping hundreds of thousands of fish in the river every year, and we're trying to increase numbers. They're also thought to be relatively weak swimmers, and we do observe entrainment for them in both diversions and dredging operations. So it's important to know what speeds and what flows these fish can handle, especially if we're putting hundreds of thousands of fish in at a specific life stage. So keep that in mind as we move along. We're also going to look at green sturgeon, another one of our listed fishes. They're also anadromous, so smaller fish will be passing multiple diversions on their way out. They're benthic fishes, which puts them sometimes closer to the inflows, also relatively weak swimmers, and they have also been observed to be entrained through diversions. White sturgeon, now a candidate for listing, for state listing. They're semi-anadromous, semi-benthic, also weaker swimmers, and they have been observed to be entrained through both water diversions and dredging operations. And finally, we're gonna look at our Central Valley fall run Chinook salmon, who are, the fall run is just a species of special concern for CDFW, mainly because they're a hatchery population, but they're anadromous and they have the lowest stream residence time, so the littlest salmon are moving past all of these diversions. So we wanted to look at them. They're pelagic and they're the strongest swimmers, and historically, most regulations are based on salmonids. And so I wanted to see how their endurance swimming compares to all of these supposed weaker swimming fishes. And so in order to look at this, we wanted to better understand life stage vulnerability. So we tested multiple size classes of most of our 4 species. Fish were placed into swim tunnels and exposed to fixed velocities for up to 200 minutes. And then we measured how long they could maintain position. We termed that time to fatigue. And then trials were stopped at 20 minutes or when a fish touched the back screen for 30 seconds, and that was their time to fatigue. So we looked at time to fatigue. We used that to create endurance curves. And from these endurance curves, we can calculate how long a fish can hold position at specific speeds. So specifically, we looked at a 1-minute escape speed. And so we were able to calculate what velocities fish were able to maintain for 1 minute from these endurance curves. We also noted fish behavior, especially things like hitting the back screen, tail propping, orienting to flow, as displaying any of these would greatly increase your chances of entrainment. So to move on to some of our data, these are Delta Smelt. We did 2 different size classes. The first size class, the 6-centimeter fishes, are supplementation age. So I think they were about 215 days post-hatch. And then our older fish, or our bigger fish, were about 520 days post-hatch, I think. So as you can see, our bigger fish are better swimmers. And we looked at this 1-minute escape speed because that's been used in a lot of previous entrainment models. We know that this is probably a conservative value, as we wouldn't expect fish to stay in an entrainment flow for a minute. But we know that as speeds start to increase beyond that, it quickly exceeds their biological capacity and really gets beyond their burst capacity. So we picked a 1-minute escape speed, and I just want you to keep in mind these values as we move along. So our supplementation age fish are able to escape at about 50 centimeters a second, whereas our older fish were just under 70 centimeters a second. Oh, and our Delta Smelt were swam at 12 degrees. All of the species, unfortunately, were swam at different temperatures, but that's based on temperatures that these fish are usually living and thriving at. So green sturgeon were swam at 18. We swam 3 different size classes. We did a 5-centimeter, 10-centimeter, and 16-centimeter fish. What I thought was really interesting about these data is that our 5-centimeter and our 10-centimeter green sturgeon basically have the exact same endurance curve and very, very similar escape speeds. And this was surprising just because of the huge difference in size at this age. However, 5 centimeters is sort of where a green sturgeon starts to look sturgeon-like, less tadpole-like, more sturgeon-like. So perhaps that's all they need until they have a next big jump somewhere between 10 and 16. I think I forgot to mention, but the horizontal lines up top are all the fish that were able to complete a 200-minute test. And we weren't able to use that for our endurance curves because that's sensor data and we don't know how long those fish truly would have swam for. We also have our white sturgeon. You'll see this in a moment. I'm probably pointing it out too soon, but our Small size class of white sturgeon was 8 centimeters, and they have basically the exact same endurance curve as our smaller green sturgeon, which is really interesting, I thought, because I love sturgeon and I'm forced to work on other species. But as we start to get bigger, our white sturgeon drop off in terms of comparison to our green sturgeon. These fish were also swam at 18 centimeters, or 18 Celsius. Finally, we have our salmon. We only swam one size class of these guys because it was part of a different experiment comparing them to swimming in turbid conditions. So these are just our control fish at 12 centimeters, and they were swam at 15 degrees Celsius. They have our fastest escape speed by a lot. So these are all of our species together. You can see that our Delta Smelt are our weakest swimmers. They were also swimming with the coldest temperatures, so sort of hard to say exactly what would be happening there. We have our stacked small sturgeon, regardless of size, on top of each other, which is interesting. And then we have our salmon, far and away the best swimmers. So not unexpected results. The small size classes of sturgeon stack. And then how do we calculate risk? So we have all of these escape speeds, but that doesn't tell the whole story. Some fish don't orient to current, and we would assume that they would be entrained. Some fish also display what we would call risky behaviors. So they slam against the back screen and keep swimming. There's no back screen in real life, so these fish would likely be entrained when there's doing these behaviors. So we ended up commandeering a model that Hoover et al. In 2005 created, where they first looked at if a fish exhibits positive rheotaxis or not. So if a fish orients to flow, we can move along in the model. If the fish doesn't orient to flow, we assume it's entrained. So fish that orient to flow, we then start to look at the velocity of the flow compared to the fish's escape speed. So if the escape speed of the fish far and away is above the velocity of the intake flow, we would assume they could escape. If the opposite is true, we would assume they would be entrained. If the speeds are similar, then we start to look at their behaviors. So if a fish displays a lot of risky behaviors, we would assume they'd be entrained. And if they don't, we would assume they could escape. So that's sort of a roundabout way of getting at the model. And then we get a number and we can classify that in our risk calculations from unlikely to inevitable entrainment. And so it looks something like this. And I know this is crazy, but we have our Delta Smelt on top, our green sturgeon and our white sturgeon in the middle, and our Chinook salmon on the bottom. So I just put up some example escapes or intake flows to put these in relative speeds that they might be experiencing in the river. I only have dredging flow intakes, but they assume that the hopper dredge that comes through the bay every so often is around 70 centimeters a second intake. So you can see for our supplementation age Delta Smelt, they are our most at-risk species. They have high risk, anywhere from 50 to 90 centimeters a second, and they would definitely be entrained by those dredging operations, which we have seen. And then our Chinook salmon are the least vulnerable to entrainment. So they are unlikely to be entrained well and above 90 centimeters a second. So this is just a good thing to be able to hand to a manager and be like, hey, these are the flows you might want to use at specific temperatures. This is a nice, easy way to look at unlikely to inevitable things. We can look at this across different environmental variables, such as salinity or turbidity or whatever you're interested in. But it's a handy dandy way to sort of pass the data along. So in conclusion, risk varies by species, life stage, temperature, flow velocity, a whole host of things. What I want you to take away from this is that smelt are most at-risk species of entrainment. I don't think that's news to anybody in this room. But traditionally our regulations are based off salmonids. And I think also everyone in this room is aware that we need to be more species specific. And this is just a handy dandy way of really hammering out what those flows should be. But yeah, so this framework can be used to inform intake flow targets for many species and hopefully help for their conservation. And I didn't do this in a vacuum. I had a lot of help from our lab. So I want to thank the whole Fungi Lab, all of our research interns for their help with husbandry, the CABA staff, FCCL staff for supplying the smelt. And then a huge shout out to Samuel Hung, who works with me closely and did a lot of these tests and is an amazing human. And with that, I'm sure I have time for questions. I have a lot of time for questions.
Great talk, and it's a really important subject. One of the things you're trying to do is mitigate risk, and it seems like using the certain temperatures that are used might not be accomplishing that goal. So for example, with Delta Smelt, 12 degrees is like wintertime conditions, but we know the Delta is regularly over 20, 22, 23, 24, which is really hard on Smelt. So I was wondering two things. One is I wonder if you can kind of just comment if there is a plan to look at this and think about climate change as well. And two, if you already have some data that might help us understand how impactful temperature is on these species. Thanks.
We have all of that for certain already, and stay tuned for smelt. This was sort of pilot smelt data because we were, I mean, you know smelt, they're hard to keep alive, to swim, to do anything with. So we just wanted to see if we could do this with them first. And then FCCL had extra larger fish, so we were like, yeah, absolutely, we'll do that too. So yes, our next steps will be different temperatures, things that are there. Yes.
I'm way outside of my wheelhouse, but instead of units of distance per second, is there any value of looking at like body length per second? Because it kind of looked correlated up to plus or minus to make some other more interesting, or maybe there's besides body length, like a more biomechanic rooted measure that would be useful.
Yeah, great question. We also have a data set that is in, or it's the same data set, that's in body length per second, but management is often in centimeters per second, and like that is how they dictate flows, feet per second often. So we wanted to put it in more metrics that are easily digestible. But yes, body length per second, scaling the exact same way. No, it's the same scale, yeah.
In terms of identifying what the risk is, might you look at where the fish are and what kinds of dredgings those fish are exposed to? So like sturgeon are going to be exposed to dredges on the bottom, cleaning out the channels, whereas they're not going to be exposed to the agricultural diversions, which are right up at the top where the fresh water is most available. And smelt, once they get adult, are going to be in salty water, which isn't going to be a subject to that. So there's ways to, I think, parameterize risk more exactly than saying that smelt are at risk, but
yes, you hit the nail on the head. Yeah, so that's the whole point of this, is that we can look at different metrics and modify it for what you're interested in and/or what parts of the river we expect them to be in at what times of the year, all that kind of stuff. So we have a bunch of different temperatures, like I said, for sturgeon. Salmon, the data is probably out there, and like I said, that was part of the different experiment. But we've done things with turbidity, temperature, salinity. We haven't really looked into depth, but that would be cool. Unfortunately, agricultural water diversions, especially not big ones, don't have flow regulations. So, yeah. Oh, great. I would love to talk to you about that. Because everything I can find says that there's just, it's free for all. So. Oh, sorry. Oh, the Zoom people, sorry. Yeah, yes, I agree with your first point, and ag diversions are hard because there's no real regulations on the smaller ones. But maybe this would be a good thing to incorporate into suggestions. But yeah. Otherwise, we can break and go to the poster session.
All right, let's take a 12-minute break and be back at 3 o'clock for the final set of talks. Thank you.
Good afternoon, everybody. Could I have everybody take their seats, please? All right, thanks everybody for sticking it out to the last session of the day. My name is Lynn Takata, and I'm with the California Department of Wildlife, California Department of Fish and Wildlife, of course, the fish. And this is session 11, Zooplankton and Other Invertebrates. Our first speaker will be Kyle Phillips from UC Davis, and he's going to be speaking about flood pulses in seasonal managed wetlands, enhance zooplankton abundances in Suisun Marsh. All right.
And then I just click, just space bar to advance. Okay, yeah, there it goes. Back. All right, thanks everybody. I'm Kyle Phillips. I'm a postdoc at UC Davis. Our crew, we've been studying zooplankton, or just plankton in general, in different habitats in Suisun Marsh for a couple of years now. And I'm really excited to present some results from a study that just got published on Saturday. So new stuff, yay. Very excited to present it. Oops. Okay, it's not advancing here, but it's advancing there. Got it. All right, so I'm gonna dive right in. This is Suisun Marsh. It's, of course, the brackish mixing zone of the estuary. About 52,000 acres of it is managed wetland, and these are kind of like understudied habitats that are a big component of the marsh. What managed wetlands are is they're diked. Yeah, they're diked habitats that, so there's like a levee around them. They pull water from this network of tidal sloughs. So that's what we're all used to sampling in Suisun Marsh. Sorry. Oh, my slides. I can't see without my slides.
It just doesn't want to.
It doesn't want to go. That's fine. I'll just go off of this. There have been recent efforts in the system to tidally restore habitats with the idea of increasing habitat for fish, which they almost certainly do, and increasing plankton production, which is a question mark. It's something we wanted to look at and test. It's not going, it's fine. I'll just go off of this. I'll just look behind me. That's okay. Yay! We'll try again.
Oh, that's why you know it.
Yeah, that's fine. Okay, are we going? All right, skipping forward. Okay, this is an example of a managed wetland. So this is Deverton Duck Club. It's about 1,100 acres. So big area, and what makes it, of course, managed is that it's levied off, and the operators, they're able to control the water stage within the wetland. And then you see kind of on the outside of that levee, you see the slough water that it's taking from, that's Deverton Slough. So it pulls water from that and flushes it through this wetland. The ideal flood cycle, if we're managing these wetlands for ducks, which is what they're principally managed for, is to flood them in the fall. Then with that, you can circulate water through them through the wet season, and that's ideal for migratory waterfowl coming in, right? That's when they're in the area. But then in the summer, what a lot of the managed wetland operators do is they'll actually dry their wetlands down. So they're essentially bone dry, and then they take advantage of all the vegetation that grows, because what that vegetation does is it produces a lot of yummy seeds that is then going to attract waterfowl the following season. So that's why duck clubs tend to do this. They flood and fall, run water through the wet period, dry in summer. And I think it's worthwhile to kind of look at how the infrastructure works, how it's plumbed. So there's these gated culverts that control water coming in and out. When the wetlands are dry, the inlets, or I should add that the gates, they act as like as one-way flow, or they allow only for one-way flow, depending on the configuration. So if they're closed, it'll prevent water from coming in during the high tide. If they're open, if say the outlet is open, it'll allow water to flow back out into the slough. To flood up the wetland, all they have to do is open up that inlet. It creates a one-way flow going into the managed wetland, so that's how they flood up. And then to circulate water, they just open up the inlet and the outlet, and then that way it's flooding up a little bit during the high tide, draining out a little bit during the low tide. It becomes a muted tidal system, and that's really interesting. And then to drain, of course, all they have to do is close that inlet, open up the outlet, and then the water will drain out during low tides. So that's the infrastructure. These are the monitoring areas that we were sampling in over the past 6 years. Currently we have access to 6 different managed wetlands. Well, now just 5, because one of them has changed to, or one of them has been restored. And then we have access to 8 tidal water bodies. So the tidal water bodies are in blue. The managed are in orange. That purple one is Wings Landing, which was restored tidally in 2020, in October of 2020. And then the year just before that, we were able to monitor it a little bit while it was still a managed wetland. So we have a little bit of before-after data. So as far as the sampling we did, pretty straightforward. Plankton throw nets. We threw in EXO water quality sondes. We collect water grabs for water nutrient data. And then we also did a rapid assessment zooplankton method, where it's real simple. You just take a bottle of water, scoop a bottle of water, run it through a mesh filter. And then you're concentrating it into a small amount of water, and then you're just counting basically moving critters that are in the water. So just like how many dots are moving around. And that's just a really quick course assessment of just what's in there before you can finally get around to looking at the tow net samples. So now getting into some results from the paper, the rapid assessments and the actual tow net sample densities were actually quite similar. So the slope between those two methods was 0.89. That's pretty close to a 1-to-1 relationship. So that was pretty great that like we can do this rapid assessment technique to very quickly characterize something. Granted, you're gonna lose a lot of detail, like you're not gonna get at species level stuff. You're gonna just get at like how many copepods, how many cladocerans, that's it. And then the other drop, or one other caveat, is there is higher error at higher values. That little picture there, that is about 1,000 or so Daphnia in a single rapid assessment sample. To give you an idea of how crazy some of these places can be. Obviously, we can't estimate that quickly in the field, like 1,000 plankton, so that's probably a reason why, the estimates are a little off. This is a timeline plot of where we sampled in the estuary over time. The main reason I'm showing you this is to show that we started sampling more areas as time went on. We gained access to new sites over time. COVID hit somewhere in there. We had to shut down for a little bit, and then we picked back up in fall of 2020. But one thing that is consistent is we did have both tidal and managed sites throughout. And then the points on here, there's some data on here already. The points, the size of the points reflects the biomass in these different habitat types. So in both tidal and managed habitats. So that's the kind of the caveat of the data. It's a bit skewed. Now, if we quickly summarize the zooplankton biomass in these habitats, if you're looking at the plots on the left there, we see that the managed wetlands support higher biomass on average than the tidal habitats. And then if we're looking at different water years, that's the set of plots on the right. We see that that earlier years, 2019, big wet year, had more biomass, but again, the data are skewed because we sampled less wetlands then. So there's that to contend with. This is the result of a generalized additive mix model. All the math is down below, but basically what you want to get out of this is explaining the seasonal densities or the seasonal biomass trends over an average water year in our data. That's going from October to September. And the main results are there's a big pulse in winter of zooplankton biomass. It's much higher in the managed wetlands. According to this model, it's about 22-fold, so about 22 times higher biomass in managed wetlands than in neighboring tidal channels. But this model also accounts for high variation between water years and between sites. So again, site differences and temporal differences. Now pivoting over to, or zooming in rather on just Wings Landing, we can see from the two top rows of figures that phytoplankton and zooplankton were higher pre-restoration. Post-restoration, it dwindled. However, the Wings Landing restoration did improve dissolved oxygen. So that's something that's a bit expected. Early on, when a managed wetland is flooded, it can also support really high decomposition, which can blow out the dissolved oxygen. And we did see that at Wings Landing, and it was the lowest there than any other site. That's the lowest observation we saw anywhere in the study. So there was at least that improvement. It's just not much food anymore. This is the composition of the zooplankton, or of the different taxa. Really, and the seasonal changes. Really, it's dominated by Acanthocyclops. That's that big orange bar in there. But the other critter that we'd get was Eurytemera and Daphnia magna, and they were pretty abundant. They were probably the most dominant taxa in all samples, but they're way more abundant in managed wetlands than in tidal wetlands. And then this is the results of an indicator species analysis, just supporting that those three taxa were more strongly associated with managed wetlands than with any other habitat type. So now, if we focus just on the data from the managed wetlands, we were also interested in basically that flood pulse, or the time when, if you flood a wetland, when can you expect high plankton production? And the reason we were able to do this was because generally wetlands flood in October. Like I said, that's what the waterfowl people want to do, is they want to flood in October for duck season. But sometimes they flood late for reasons like maybe they have levee problems or something, or sometimes they'll flood early to try to flood out invasive weeds. So we have some instances of data like flood starting at different times. We found, using this model, we found that regardless of when a wetland is flooded, the peak abundances on average were about the 2-month mark. So you could expect after about 2 months of flooding, you could usually expect a big copepod. This result, of course, is also very, or not very, there's like a bit of a threshold response with chlorophyll A. So when chlorophyll is really low, then that does, of course, shut down copepod abundances in the wetlands. But once you get above, God, it's only like 10 micrograms per liter, then it's good. Then it gets pretty good for copepods. Cladocerans, so that's again mostly the Daphnia. They had a similar thing. It didn't really matter too much when you flooded a wetland. In general, they would peak after about the 4-month mark. Or 122 days was the peak there. However, they were super sensitive to salinities of course they are, basically anything above 8 ppt. So if a wetland is getting above 8 ppt in salinity, it's not going to support Daphnia because that's just too toxic for them. That's above their threshold. So those are the model results. And now I want to come back kind of to this conceptual model of how the wetlands move water, but now let's throw some plankton on top. So you start out in the dry phase. There's only water in the sloughs. Ponds or the managed wetlands are of course dry, but there's a lot of plants in there. And presumably there's some resting eggs in there from the previous season. Now suddenly you wet it up. What's going to happen is plankton are going to be imported in. Any resting eggs that are in the wetland are going to hatch. While that's going on, there's all the decaying vegetation. So all those plants that were grown for waterfowl, they start decaying. They start releasing a bunch of nutrients. That creates a big phytoplankton pulse. That then stimulates zooplankton production. And then on top of that, managed wetlands, because they mute the tides, they probably hold water for a bit longer. So they extend the water residence time. And so by extending the water residence time and just giving the plankton enough time to actually cook and just accumulate, with all that in combination, it probably all that in combination leads to high and ideal conditions for zooplankton. And then of course water that's draining off of that while it's circulating, releases plankton-rich water into the sloughs where fish can habitat or where fish can access it. Fish can also go into the pipes. We do get them in the managed wetlands. It's not a super hospitable place for a lot of fish, but some do make it in. So really, if you're focused on what's being exported and what's coming out, that's where the value in this process might be. And then last thing, so implications, right? That whole process I walked you through just now is essentially the flood pulse concept in floodplains and natural floodplains. So really, we think of managed wetlands as just floodplain analogs, but the advantage is you can control it. We can decide, oh, we're going to flood this now, and then maybe 2 months later, we'll expect a little copepod boom. That could be really useful for fisheries management. The thing is, we do in future studies, we're going to work on this. We do want to see like what other, if you do that, does it create that effect? And then also, does that does that cause problems for other things? And then this is Grizzly King and Tule Red. So this is a managed wetland right adjacent to a restored site. The Grizzly King in water year 2023, not included in this data set, but in future data sets, had really high copepod abundances. And the thought is you could just add a little gate between those two habitats and increase plankton production in Tule Red occasionally. And that's it. That's all I got.
Thank you, Kyle, and I'm sorry for the technical snafu there. We have time for a question. There's one in the back there, or one in the middle.
Kyle, this is super awesome. It's fun seeing your research, findings come to a published paper. My question is, we know that not all managed wetlands are the same, just like all tidal wetlands aren't the same.
Right.
So I guess I would love to hear your thoughts on where it's located in the context of the landscape. So Potrero Pond that you showed, that's at the terminal edge of Denverton Slough. And so it's kind of like the upper end of a slough, and then it's been lopped off, right, for managed wetland.
Right.
And then some of the wetlands, the tidal wetlands, are more like at the mouths of places that have lower residence time. So I was just wondering if you could kind of elaborate on, are you seeing that pattern of where you're sampling, whether it's within the wetland or where it is in the channel itself. If that residence time is, you're seeing that pattern come out between residence time and zooplankton production across both types?
I would say, so the residence time in the wetland is going to depend on that circulation rate, right? How much is flowing through it. So that's in the wetland. But as far as like what's coming out of it, right, it's going to be very dependent on what slough it's dumping into. And then that, you know, what's coming out of it is going to disperse at different rates depending on where it dumps back into the tidal system. Did that answer your question? Sort of. Okay.
All right, well,
All right,
I
we're
think,
good.
I'm sorry, we're gonna have to move to the next speaker. If you have any questions, I'm sure Kyle will be happy to chat with you at the poster session. Our next speaker is Dan Ellis. Dan is a senior environmental scientist in the IEP Synthesis and Management Group. He's passionate about wetland conservation in ecological models of invertebrates and their predators. Take it away, Dan.
Everyone hear me all right? Okay. I recently found out that I can take my time with this talk, so we might have some time for questions at the end. This project is a culmination of a multi-year effort with a number of different scientists from a range of the IEP agencies. The goal here was to look at the integrated IEP zooplankton data, so not an individual survey, but all of them together. And we were looking for the gaps, the strengths, and potential redundancies. So the goals we had in mind were, first, we wanted to understand those gaps and those strengths. The asterisk is there here because power analysis isn't really perfect for looking at strengths. And with that in mind, we did directly address redundancies, the strengths, by using a second method. We wanted to consider the full community. So the longer we've looked at the system, we understand that it's not an individual taxa that's driving our fish food webs and the broader food webs. And the final piece here is we really wanted to consider different combinations of space and time. We know that you, the data users, the managers, are expecting to use this data in different combinations, so we wanted to approach it and take that into account. This is the community that I'm talking about here. We got a lot of stakeholder feedback, and we ended up going with the meso and the macro zooplankton communities. We did not do the assessment for the microgroup. And so for the rest of the talk, I'm going to be talking about the mesozooplankton. So between 150 microns to the 500 micron mark. And we'd be happy to share about the other stuff. There just isn't time. Okay. So if we're going to look at power and we're going to look at redundancy, we have to have a specific question in mind. That means we want to think about what that question is going to be. We wanted to come up with questions that were broadly applicable for the IEP community. And the first is just plain and simple. Can we use the data set we have to track changes in abundance through time? And I'm calling into or drawing attention to what would a small effect size be and a large effect size. So if you can imagine there where that big drop-off happens, I probably don't need to collect as many samples to characterize that drop-off as I do for that very small reduction there for the small effect. And we'll talk about that later. The next thing is we obviously want the managers to be able to use these data to relate it to other features of the environment. And so that means, in our case, flow. So we took flow as an example, and we wanted to know, can we detect a relationship significantly between abundance and flow? So I'm gonna be coming back to this diagram a lot because this was multiple people's time over multiple years, and we tried to take a comprehensive approach, and it was a little confusing. So hopefully this diagram helps a little bit. We took the multivariate data set and we aggregated it in space and time. We decomposed it with a principal tensor analysis, and that produced a community dendrogram. And then from that community dendrogram, we selected our representative taxa. The idea here was that the power analysis, the redundancy analysis require us to do univariate stats, but here we are wanting to understand the full community. So our approach was, let's first identify good representatives of that community. We'll run it on that subset so we're not using trillions of hours of computer time, and then we'll see what the outcome is. So jumping into results here, for the Mesozooplankton community, these were the representatives that were selected. Now, our initial intent was to look at the statistics, bring it to our stakeholders, and see if we needed to tweak it a little bit based on our understanding of the biology or perhaps the importance of a particular taxa. But in the end, the 6 representatives that we selected were only five out of the 6 were all supported by the stats alone, and one of them, there were sort of 2 arguably equally good representatives. And so Daphnia was the one where we didn't select the alternative because it was only slightly less representative of its cluster, but it had such a great value to the fish food webs that we care about. So we have our multivariate data. It's been decomposed. We've got our representative taxa. Let's start doing some analysis. Power analysis. We ran thousands of combinations of power analysis so that you don't have to. We considered 3 spatial scales, 3 temporal scales, sort of 4. Effect size. Effect size is how much of a difference you expect to find. We considered 4 of those. All of them were based and grounded in what we see in the environment. And we looked at the response variables, abundance alone or the relationship between abundance and flow. So I want to make sure we all have a strong foundation in what power is. And so in a power analysis, what you're doing is you're taking the data you have and you're doing simulated random draws. You're imagining if you had only taken 3 samples, what would your estimate of abundance be? If I had taken 4 samples, 5, 6, etc. But eventually you get to the point where every extra sample you add doesn't change the average that you're producing for that abundance. And that's the asymptote. That asymptote is where you now no longer need to take more samples. Beyond that point, you might call it redundant, but that's why I'm saying it's not really a direct test of that. Anything to the left of that, and you're not able to significantly detect a response. So I'm going to be showing you a number of figures, and the general premise is I'll show you the individual taxa and then a combined figure for the full community. And anything below this line is low power. Anything to the right of this line is where we put in where we're at, the amount of samples we're actually collecting. So anything to the right and up of that is where we don't have enough sampling. And finally, this is our sweet spot. This is a spot where we currently are sampling enough that we can detect these trends with a significant observation. So here's just 4 examples, and I'm going to start off with Daphnia up there. If you notice, we reach our asymptote for all 4 of those effect sizes within our top left box. So that means that we have really good confidence in that data for that specific taxa. You can see, though, we don't have the same thing for hyperacanthomyces. I won't even go and say that. Hyperacanthomyces longirosteris. We don't have that same quality of data. So right here, this sort of tells you already, it really matters which particular taxa, or if you care about the full community, whether the data set will be appropriate. And I want to show you an example here with Hylella because not all taxa are present in all regions at all times. So you can't run a power analysis if you don't have data. If the catch is so low that you can't run the data, we had this scenario, and that will come up later. So this figure, again, represents thousands of combinations. We think that it is something you could apply to your own work. In the first column, we have our spatial scales. We consider the upper San Francisco estuary as a whole, 4 regional spatial breakdowns. I think it was 11 subregions. For temporal, we did year to year, month to month. When we were looking at our flow abundance relationship, we, at least at the upper SV wide scale, we considered both a 5 and a 10-year value because we might see an effect with flow over a shorter time span versus a longer. And for regional, we did it just for 5-year. And then these are the 4 effect sizes we considered. So you can roughly think about the effect size of 0.1 as a 15% change in abundance over whatever that time span is in the given subregion or region, up to 85%. And again, these were all grounded in the biology. So the first grouping of responses we found, and this is community-wide, these were situations where we could not assess the full community. So like I showed you there for that power analysis, we just couldn't do it maybe for all of them. But even when we could do it, we didn't have full power to detect trends across the community. The next group was when we couldn't do the analysis for every combination, but every single combination we could run, we had power for. So I think of this as, I feel pretty good about it, but there's still questions about the level of confidence you would take away. And we had two spots on this chart where we sampled and we could fully assess the full community and we had the power for it. So this is what that figure looks like. The color of the blue, the intensity, is the proportion of those 6 taxa that we had power for. And you can see that there's a general trend that, and this is pretty much what you'd expect, larger spatial scales, longer time spans, and larger changes in abundance are going to be easier to detect. And in case any of you are wondering, yes, we did the stats on how many samples you would need to add to get where you want to go. So for example, in some places you're there at 0. For example, upper SFE for a year-to-year data set, if you wanted to get all effect sizes, you would only have to add 25 samples. But if you want the sub-regional data set on a year-to-year basis, you're looking at adding about 5,000 samples a year. Okay, so we've done our power analysis. We have a really good sense for where the data are strong. Now we get to something a little bit more touchy. We want to think about where we might have redundant sampling. Where can we reallocate sampling effort? Where can we be more efficient as an IEP community? And in this case, we took a different statistical approach that was much more time intensive to do. It was a Bayesian approach with a hurdle model. And for that reason, we couldn't do as many combinations. We considered these groupings. So for space, we would break up our data and we would do artificial sample reductions. So we have the full data set. We're going to create a model from that. And then we're going to do a partial sample reduction. And we're going to make another model. We're going to compare the two. We did 10% reductions, 33%, and 67%. So really it was a third, 2/3, or 10%. For time, we couldn't do 10% because we were breaking our data into seasons. So the question was either did we remove 1 month or 2 months from that given season? And so again, I'm going to show you a specific taxa, and then I'll show you what it looks like for the full community as a whole. Here, this example is Pseudodiaptomus. In this case, there was really high overlap between the two models. Lots of variation though, notice that? But in this case, that is where it would fit in as a single point on this figure to the right. So that's kind of what it represents. Again, many, many model combinations, hundreds and hundreds of model hours run. This is what that looks like combined across the community. On the y-axis, you're looking at the percent overlap of the models. And I hid this from you. We had the model both estimate the direction of the change and the actual CPUE that it thinks it would have. And as you can see there in orange, that's the trend. The trend tended to be a little better than the specific estimate of CPUE itself. So when considering redundancy, if you only care about the direction of the change, we have more redundancy in that context. And I would argue that we have a little bit more redundancy in the spatial data than the temporal sense. So for example, if you were looking to reallocate samples, I personally would not be taking them from how frequently we collect them. I might maybe change where we collect them. But I want to pull your attention to the percentage of overlap, because with those error bars, it's the range is very high. So for an example, if I do a 1/3 removal of the data on a monthly time scale, I'm looking at, what is that? About 35% model overlap to about 85%. So if I do that reduction in a given year, there might be an 85% overlap in the models, or there might be a 35% reduction. We don't know what data we get year to year. And so that's the range of plausible scenarios that would result. So we took our multivariate data, we decomposed it, we picked our representatives, we did our univariate stats. Now we brought it together to give you these color diagrams that kind of give you a sense of the full community. And my takeaways here are this. A lot of us might be asking, like, is the data good enough? Is it redundant? Can we reduce sampling? Should we increase it? It depends on your question. If you care only about a particular taxa, we've got that data, we're happy to share it with you. If you care about the full community, we've got that data, we're happy to share it with you. It matters the spatial scale, the temporal scale. How big of an effect size do you expect to see is a huge factor for whether or not you have the data to collect it with what we got. And again, the response variable. If you're only interested in the change in abundance, that's one thing. If you want that relationship, that's something different. Next, really, we all know this, but we maybe aren't all doing it. We should all be doing power analysis for our questions. And with that in mind, we are here to help you, and we have probably already done it. So if there's a particular region or taxa, and you're wondering, and you're about to go down that road to, I'm gonna do this whole analysis, don't bother if the data can't detect a significant trend, because what's the point? So we're here to help you. We would love to share what we've done with you. And with that in mind, we've got a manuscript that's been submitted, and we're also working on an IEP specific guide that's meant just to make this data set easier to look through, because it is pretty comprehensive. And with that, I really want to thank our funders and everybody who's contributed.
All right, we've got time for a couple of questions.
And any plans to provide the community with software? Maybe AI-driven software to do this? AI assistant, sorry.
Yeah, I don't think I do. I don't. You think AI could do this? Well, like replace us? Yeah. Yes. You're talking about like presenting the data then? That we probably could do.
No, just for doing power analysis.
Oh, yes, yeah, certainly.
To provide a power analysis to allow people to figure out what sampling effort to put into something.
Gotcha. Yeah, I think the answer would be
I helped Dan on this project, and it would be relatively straightforward to write, like, all the code is already on GitHub. It would be relatively straightforward to turn it into a user interface. The one caveat being, it does take a long time to run the simulation-based power analysis, and even longer to run the Bayesian redundancy analysis. So, you could put in, your region of interest and the data set you want to test the power of. You would just, have to come back tomorrow for the answer.
Yeah. And I'm just going to throw this up as a teaser. This is the macro invert one.
All right. Our next speaker is Bryan Barney. He's from the California Department of Fish and Wildlife. In his free time, he likes to keep reef aquariums, 3D print, and do some 3D printing. He's going to tell us about his research on golden mussels and monitoring. I can get the slides up. Oh.
Is that one?
Oh, no. Just shut that one.
So, is it that one? Oh. Oh, that's
okay.
That's
all right.
Come to the realization through the day that I've used a tragically and unintentionally misleading word in the title with model. I don't mean a mathematical model. They're just going to talk about an example to follow for how we should go about doing something like proficiency testing or lab intercalibration.
And thank you for the introduction. My name is Bryan Barney. I'm a fisheries geneticist from the California Department of Fish and Wildlife. eDNA is one of the things that we do. We also do all sorts of genotyping, genetic stock ID of hatchery fish, provide genomes, provide all sorts of genetic resources for the fish that we manage in the state. So if you have questions about the genetics lab, come talk to me. But today I'm here to talk to you about a kind of an interlab effort that we've been undergoing, looking at the recent invasion of golden mussel and how we do eDNA monitoring across multiple agencies. As all of you are probably very well aware, we have an invasive species in the California waterways, the golden mussel. And it is invading through waters that multiple agencies are responsible for. So these agencies are doing their eDNA testing in their own in-house laboratories. And they may be doing it in different ways. And so this is one of the reasons why we're going about this lab intercalibration process. We're not the first invasion of golden mussel out of Southeast Asia. It invaded in, I think it was 91. In South America. And we know from that invasion in particular that this is a very rapid spreader. It's one of the species that's a very successful invasive species. And so our concern is that the impacts of this as it forms these massive mats can be great in terms of things like impacts to infrastructure, biofouling, recreational impacts, public health and safety impacts, ecological impacts of this endangered species, or this invasive species, sorry. Ooh, too bad it's not the other way around, what I just said. Like I said, we have multiple laboratories that are doing eDNA work on this. And so we, the California Department of Fish and Wildlife and the Aquatic Invasive Species Group has put together what we call the Golden Mussel Monitoring Task Force. And I am working with these laboratories, the Southern California Coastal Water Research Project, CDFW, Bureau of Reclamation, the Metropolitan Water District of Southern California, DWR and USGS. If you are in this eDNA task force and I forgot to mention you, I apologize. But these laboratories are all doing eDNA testing. Each one of us does it a little bit differently, however. And so one of the concerns is about standardization. There is a growing call in the literature in eDNA about standardizing the use of eDNA for monitoring, whether it's an invasive species or rare species, whatever it might be. And there's even an international standards organization, or ISO. There are a couple of documents in draft right now to try to standardize the process of water sampling or extracting DNA from those water samples, two different documents. So the idea of the standardization is really gaining a lot of traction. However, if you're an eDNA practitioner in any way, you kind of have come to realize that eDNA is not always a one-size-fits-all situation. There's a lot of variation that we make and choices that we make on how we do or how we build an eDNA assay that are very specific to our target. And even within that, there's a lot of variation in the way that we do things or the instrumentation that we use that can give us different results. We may run the same sampling technique, we may do the same DNA extraction methodology, but if we use two different instruments, two different thermocyclers from two different manufacturers, we might not always get exactly the same results from two different labs. So there's a lot of variability that's out there. I'll show you one, even one of them might be the qPCR assay that you use, right? So qPCR is a quantitative PCR, it's the act of trying to measure how many molecules of the organism are in the DNA extract that we have. And for golden mussels, there are 4 different qPCR assays that are out there and available right now. We have decided on this bottom one as a group to use. It's by, I'll say, PIA in 2017. But there are other labs that use some of these other assays that are out there. And then even one more choice that can lead variation in what a different lab may say on any given sample is the heuristics for what we refer to as a positive detection, right? How do we make the choice if the sample is a detection or not? Usually when we get a sample, we'll sample it with a certain amount of replication. Do we decide that all replicates have to be positive in order for us to call that a detection, or any one of those replicates is positive for us to call it a detection, or somewhere in between? This tends to be more of a management decision, leaning towards being acceptable of false positives or acceptable to false negatives. So I think I've painted a picture of a lot of variability, and so is this questionable to you? Like, if you send it to one eDNA laboratory, will you get a different result from the same sample? The way to go about answering that question is intercalibration or proficiency testing, which is a little bit more aggressive than intercalibration. And this is a process that we're going through right now with those laboratories that I mentioned that are on the eDNA task force. The idea is that each lab tests the same samples blindly. Somebody has to make a blind plate of samples, send them out to the laboratories, collect the data, and say, like, yeah, we passed, or, you know, compare what those results are. If we find differences in those results, we discuss it and try to figure out what the origin of the difference of those results might be. Try to harmonize if we can, which is challenging because we're all different government agencies and we're all different DNA laboratories, and so we all have our preferences for how we do our eDNA testing. And then repeat this until we get to that point where we kind of all agree and we think that we would get the same answer, given whatever laboratory tests the sample. So we have done this, and actually this is hot off the press data. I literally got the last piece of data on Friday. But in order to do this, we sent samples out to those laboratories. We made samples at 3 different concentrations, 12.5 microliters, or 12.5 copies of the target DNA per microliter, 2.5 copies per microliter, and 1.25 copies per microliter in 2 different matrices. One of them just a water matrix, and then one of them a lot more representative of what an eDNA extraction would normally be. You go out into the field and you take a sample. It's not just the DNA of your organism that's in there. There's all the other organisms that are in there, bacteria and fish. And so maybe the assay behaves differently in a quote unquote real sample matrix. So we buy from a DNA synthesis company a synthetic gene. We call it a G block in the field, but it's a synthetic gene that has the sequence that our assay is for. And we spike it into samples at these concentrations. We provided each lab 4 iterations of that, and we asked them to test each one of those samples 5 times in quintuplicate and tell us the results. So again, we provided them we didn't provide them with this layout of the plate because it's supposed to be blind. And let me show you the results that are not terribly exciting because everybody detected it. Hooray! So I just explained to you, like, labs are different and everybody gets different answers, but it turns out in this particular case, mostly because we all use the same qPCR assay, we get there differently though, which is interesting. But even at the 1.25 copies per microliter limit, by the way, we chose that one because that's CDFW's assay's limit of detection. So that's what you get for being the one who runs it. But everybody was able to detect all of the samples that we provided. One laboratory in particular, this is the Southern California Coastal Water Research Project, or SCWRP. They use a completely different methodology. This is called digital droplet qPCR, and it is really, really, really good at calculating the amount of copies in a reaction when it's very, very small. Quantitative PCR is pretty good at it. Digital droplet PCR is amazing at it. They use it in the medical industry. So even though we tried to get to 12.5, we really got to probably about 20, et cetera. So, but it's nice to understand that we can dilute samples and real close to what we think the number of copies should be. We also provided everybody with blanks. So everybody can detect it when it's really there. What happens when it's not there? And this is interesting. This is, I think, when the heuristics come into play. That the thing that I mentioned about how many positives does it take out of all of your replicates to call a sample a true detection or not? And I think this is much more of a management decision than a scientific one. But labs may have words like retest. We would retest the sample because maybe 1 out of those replicates was positive. And what's interesting to me out of this data set is from the SCWRP data, it apparently is true that maybe there was an incredibly trace contamination of something in our water blank that we used. I don't think it's enough to affect any of the true detection results. It's multiple orders of magnitude less than that. But still, if it's, 0.11 in that one sample, the bottom right data point there, that would be 1 copy every 10 microliters of DNA. And so that would occasionally pop up as maybe a positive across multiple replicates, which is what we see in that. So we also ran sample extractions, and our sample extraction was, we've been doing golden mussel eDNA testing, and we took all of the samples that we thought were negative based on our assays, and we pulled them all together, and that's what we spiked the synthetic DNA into. So at the same concentrations, everybody detected it, and we got similar concentrations from Squirt's digital droplet PCR device as well. But the story is that maybe we have a little bit more contamination from the background in our sample matrix than we have. So we are going to be rerunning this, specifically with focusing on the blanks to make sure that we can cover that. But the difference that you see between CDFW being no detection on the blanks is that we have made the decision on our end to be very cognizant of avoiding false positives. We don't want an eDNA result that may or may not be real to spawn a lot of activity that may be a technical problem, right? So we have made the choice, the managerial choice, to say, I want to make sure that it's truly there before I do anything. Other labs may have made a completely different choice. I want to know the minute, maybe I want to know, because then we will act. Let's see, what else can I say? This work is ongoing. This is, like I said, we literally just started working with this data. This is intercalibration now, but it's probably going to turn into what we call proficiency testing, where in the future, other laboratories, not just the ones that are doing their own testing, but maybe external or private genetics laboratories, we would send out these plates for them and then score their results, and then I'll put it in air quotes, but qualify those laboratories to be qualified to do invasive species testing for these individual, in this case, golden mussel, but maybe multiple species down the line. So we can all detect it down to 1 copy per microliter. That's good. We all have proficient and functional eDNA laboratories. Everybody's pretty good at their jobs. We might have a little bit of difference in terms of what we call a detection, and that seems to be much more obvious at low amounts of DNA than it is for true detections. We seem to have harmonized on this PIA 2017 assay, kind of somewhat accidentally. CDFW and DWR initially, in the immediate response to this, we talked and worked together to use this assay, but other laboratories have seemed to be coming on board. But not everybody. One of the labs that participated in this adopted this assay, but that's not what they usually do. They would usually just run a normal PCR and then run it out on a gel and look for a band. I mean, that works too. It's just not super quantitative. And so what I'm hoping to have presented is the idea that when we have multiple agencies, everyone has their own laboratory or their way of doing things for testing. It's probably a really good idea to perform some kind of a lab intercalibration, or maybe go on to this idea of proficiency testing, because these different assays, different instrumentation, they can have all sorts of variability. And it may not be that I test it and I get the same answer that you do when you test it. And yeah, that is what we're going through right now. And I would appreciate any questions or comments about the intercalibration process.
All right, thank you, Bryan. We have time for a question, maybe 2.
Anne.
Hi, this is great. It's really nice to see this stuff, and I know it's really hard work. I had a question about how the assay is set up, because when you have those really low copy numbers, sometimes it can be more consistent if you're using more template,
yes.
But it wasn't sure, like, is that something that the labs were allowed to kind of choose how much template they used, or did you require them to use a certain amount?
That's a great question, and I'm sorry I skipped over that in this. Each lab did the assay the way that they would normally do it themselves if we weren't doing this process. So typically we run a 20 microliter reaction in the CDFW lab. 4 of that is template when we run. So even though it's like 1.25 copies per microliter, there's really 5 copies on average in the actual reaction. Different labs had different amounts of template that they would add, and that was still worked out in this data that it was sensitive to the same levels in all cases. Other laboratories had completely different recipes for how they run this PIA assay. The fun thing about that PIA 2017 publication is that as published, it's wrong. There's something wrong in their actual recipe for running the qPCR assay, and so DWR and CDFW had to work together and kind of figure it out. So we've set on a series of reaction conditions, but the Metropolitan Water District runs a different one, and the Bureau of Reclamation runs a different one. So the assay itself is pretty robust to changes, which is nice. Lucky.
I think we have time for one more question.
So DFW is not wanting a false positive to get out. Could you delve into why that is? And could you also, what are the possibilities of a false negative? And how are we avoiding?
Sure. Conjecture on my part. This will be a little bit of conjecture on my part, just not policy or anything like that. But even though eDNA is not a regulatory method, right? And so a positive result in an eDNA assay is not necessarily regulatory. There may be some optics about it where when we say something is positive for a location, actions should happen, right? Maybe increased boating restrictions or increased monitoring or all sorts of things should happen if we report something as positive. So we made the decision to be like, we're making sure it's absolutely positive before we say anything about the positivity of a sample. Other organizations may be very concerned about like ramping up their real monitoring of like villagers in the water if they get even a sniff of golden mussel that's coming their way. Like Metropolitan Water District of Southern California is very sensitive because they can see the oncoming storm in terms of the eDNA positive results making its way down to them, right? So their decision reflects that. If they see any one of their replications of the samples as being positive, they'll call that a detection and they'll act. So that's that dynamic of, it's not that we don't want to act, we just want to make real sure that it's really there before we act versus.
Really sure that delays the reaction.
It can. Yeah. Above my pay grade, I'll say.
All right, well, thank you very much, Bryan, and I'm gonna hand it over to
All right, thanks for those excellent presentations today. The rest of the day until 5:30 is slated for the second poster session. Again, top of the stairs, take a hard left. As a reminder, there is an after hours event organized by Peter Nelson at Sacramento Pipeworks. It's climbing followed by some beverages. If this is the last day that you're attending, please drop your badge holder at the registration desk and it can be washed and reused next year. Just a heads up, if you're at all interested in being my co-organizer next year for the event, please let me know. It is work at times, but it's very rewarding and it's great to see this play out. And I'm looking for somebody to co-organize next year, possibly take over as head organizer in 2028. And with that, I will see you all tomorrow.